Hello, welcome everyone to the course, How the Internet Really Works. My name is Lindsay Ventimiglia. I'm with O'Reilly, and I will be your facilitator for today. Today, we welcome your instructor, Russ White. Russ has experience in designing, deploying, breaking, and troubleshooting large-scale networks and is a strong communicator from the whiteboard to the boardroom. He has co-authored more than 40 software patents and participated in the development of several internet standards, helped develop the CCDE and the CCAR, and worked in internet governance with the Internet Society. Russ has a background covering a broad spectrum of topics, including radio frequency engineering and graphic design, as an active student of philosophy and culture. You can learn more about him by opening the bio widget at the bottom of your screen. I will turn the program over to Russ in just a moment, but I would first like to cover a few housekeeping items to help you get the most out of today's course. At the bottom of your screen, there are a series of icons. This is called your widget tray. There are a few ways for us to interact with each other during the course. Please notice open on the right-hand side of your screen is the resource widget. And then below that is the attendee chat where we can communicate and interact with each other. In the center of your screen is a slide window, and below that is the Ask a Question widget for questions. And then for those of you that are subject to regulated status, the chat feature should not be used. The audience may include customers, vendors, or competitors of you or your employer. If you do choose to take advantage of the interactive features available in the course, and we hope that you will, you are responsible for any information you choose to share. We are recording the course, and we will have it ready within 24 hours after we've completed. Tomorrow, we'll be sending an email letting you know that today's recording is available. The recording for today's session will also appear on that course landing page. That's the same way that you entered the course today. It'll appear there once it's available on the right-hand side as session 1. Also, in your widget tray is a 3-bar chart icon. That's the course feedback survey. So if you have time during the course, please do let us know what you thought about it. Otherwise, we'll give you an opportunity when we end. It will pop up in the center of your screen. And now, without any further delay, I'd like to turn the program over to your instructor. Please welcome Russ White.
Well, hello, everyone. We're kind of a small group today. Maybe that's because it's getting towards the end of the year and people are tired of hearing me talk. That could be. Who knows? So, anyway, all right, let's see. I do try to watch the attendee chat and the Q&A. Actually, maybe I should move these. Well, it's kind of hard to do that. But anyway, so I will try to watch those from time to time and see what's going on, see if I can answer any questions that you might come up with. This is kind of a new set of slides because we used to have a 6-hour course on this. Well, 2 3-hour courses from 2 days or two months. So we made this into a single 4-hour course. And if you look in the stuff that you can download along with the slides, there is a Word document PDF. I'm not sure if they converted it to PDF for download or if they just left it as a doc file. But there are some what I would call lab exercises for this course, which are really just things like, okay, so you've gone through this class and you want to be able to actually look at DNS a little bit on your own, or you want to mess around with stuff and see some of the things that we talk about here. This document will give you some information about how to do that stuff. So I'm going to go ahead and kick off my screen sharing. As usual, we will take a break at the beginning of each hour, like 10 minutes before. We will jump off and do a little bit of a break because my voice needs a break and you need a break, and you're going to need chocolate and other stuff like that to keep you going. Lindsay had a tea earlier. You might want to go grab a tea or something, I don't know, as we go on. So let's begin here. How the internet really works. So I began this set of slides many, many years ago, and I was working for VeriSign, and I was asked to do a presentation to a congressional committee about a U.S. congressional committee about the ecosystem of the internet. Like who pays for what and why? Because a lot of people in government didn't understand or still don't understand, like what are all the bits and pieces that have to work in order to make the internet work? It seems so simple. I plug into the wall and boom, it just works. Well, it's not really that simple. So let's see. This is what we're going to try to cover. We're going to start with the domain name system because this is your primary interface to the internet by and large. And I think I have something messed up. So jump over to another screen real fast. Look at that. Yep, it's messed up. That'll be better. Anyway, and then we're going to talk about the email system for just a little bit, not a ton, but just to give you a sense of the email, how email works. And then we're going to talk about internet routing, which is probably one of the most technical parts of this presentation. And then we'll talk about providers and peering, and a little bit about the advertising ecosystem and what Shoshana Zuboff calls the uh, the whole idea of was it behavioral excess and uh, surveillance capitalism. Then we'll talk about the reshaping of the internet, what's been going on recently. I noticed that the FCC has been pushing a little bit about net neutrality again. So maybe I don't really have slides for that, but maybe I'll talk about it a little bit. And then we'll talk about internet organizations and what those internet organizations are and what they do. So, so that is where we will go with this. And hopefully you'll hang out with us for all 4 hours. Remember to check or to use the Q&A and or the group chat. I'll be trying to watch both of those in between slides. All right, so let's get started. This is the whole internet. You might remember there was a TV show once where they tried to convince a young lady that the entire internet was in a single black box, and they had it around the couch and they had lost it or whatever it is. But this really is pretty much all the basic parts of the global internet, minus standards bodies and organizations. This is just the parts that deal with how traffic actually flows through the global internet. You'll notice that I have a DNS ecosystem over here, the access ecosystem, what I call the DFZ, or the default free zone. This is where you do not have a default route. And then you'll have registries and names and numbers primarily over here on the left side in this unlabeled greenish box. So this goal of what we're trying to do today is we're trying to get from a host connected to an access provider through a transit provider to a content provider and get the response back. That is the goal of the internet, is to get packets back and forth. There's a lot of stuff that goes into this. It sounds like a very simple goal and something that would be very easy to do, but it takes thousands of people with thousands of different skill sets, a lot of money and a lot of time to make this work. So the goal here again for us in this live training is to just walk through each of these pieces. We'll walk through access providers, DFC, the DFZ providers, type providers like IXs and transit providers. And then we'll talk about DNS, how the DNS works. Again, we'll start there. And then this is the organizational part up here when we talk about these types of things. So let's begin with the domain name system. Let's see, South Park. Yeah, that was it right there. All right. So the domain name system is one of the two ways that most people interact with or see the internet. This is a common way that people understand the internet. So the way the DNS system works, or what the DNS system does, in effect, is it is going to act just like some sort of a street map application, whether you're using Sigic or Google or Maps.Bing or whatever it is, it's Waze or whatever. This is basically a street map system. What DNS is going to do is it's going to give you, you're going to look up the name of a business or a service. So we often get these confused, but in DNS land, DNS records do not represent IP addresses, they represent services. It just so happens the most common service is an IP address. But you know the name of the service and you want to know how to get there on a map physically. You know, you're looking for Big Mike's, and well, it's by the Dollar Tree and the Home Goods out on 64. You drive past Longhorn, you go down, and Big Mike's is back there in that shopping center. And yeah, Big Mike's is a real business, so you can go look it up and see if they're around. I don't know if they still call themselves Big Mike's, but they make great briskets and they have great burn-ins on Tuesdays, if you ever go by there on a Tuesday. Anyway, and this is in Apex, North Carolina, so you have to be in North Carolina someplace, as you can see. But anyway, the idea is to convert a business name or a service to a physical or geographical location so that I can find my way to that service. We need the same sort of thing on the internet. Each service on the internet lives on a server in a physical location which is connected to a topological place rather than a geographical place. It actually has a geographical location as well, but it has a topological place on the internet where it is connected. I need something that's going to convert these two things from one to the other. This is what the DNS does. Now, one kind of name in the DNS, in the domain name system, is what is called a URL, Uniform Resource Locator. This is a subset of what's called a URI, and this is what we'll mostly be working with URLs today. So an URL is made up of several parts: a top-level domain, a subdomain, and a service or a protocol. Now you might notice that the URL is read from the right to the left. This is not because the person who invented DNS was Chinese or Japanese or Hebrew or whatever, where you read from the right to the left, but rather because they thought that when you were typing something in, if you type in HTTP first, then the browser could actually say, well, you're only looking for things that you've looked at in the past that start with HTTP. If you type in www, then it can narrow it down. So this is how you get auto-completion in a browser, is that you actually start by typing in the more specific information in a right to left language, like English, French, or Spanish, and you move to the right with less specific information so that the browser can search on the more specific information. Now, you also have to remember that these URLs were invented when there were only 5 or 6 top-level domains. So there really weren't a lot of top-level domains to be searching among. Today, we have hundreds of top-level domains. So maybe this doesn't work as well in the modern world, but that was the original idea. So each one of these sections between the dots represents what we would call a zone or a domain. It's, well, a domain or a subdomain, but a zone. So for instance, .com is a top-level domain or a top-level zone. Then you'll get to WP Engine, that is a zone, and then all this other stuff, .com, like Bing.com, will bring you to a zone. Images.bing.com is a subdomain or a subzone of the Bing.com domain or zone, and you'll see it goes all the way down. So this is what it comes down to. Now, a zone is an administrative domain. So everything normally to the left of a given dot is within a single administrative domain. So that is the way it works. So .tech itself is an administrative domain. Rule 11 is an administrative domain. Well, www is a subdomain that is actually part of this domain, but then you have HTTP, which is your service or your protocol. So one thing you'll notice is in the modern internet, we often don't have this. We don't have a subdomain that is a service or a service level, a service indicator on the subdomain. The reason for this is because we now do reverse proxies and stuff like this that allow us to say, I'm just going to go to rule11.tech. If there are 3 different services like a web server and an FTP server and a mail server at rule11.tech, I'm going to assume that because I'm using a browser to get there, the server itself will say, I'm talking to a browser, therefore I must be looking for the www service on this particular server. So let's talk about how DNS works. Let's see. Yeah, let's talk about how DNS works for a little bit. All right, so you go to your web browser, and trust me, if this is all very familiar to you, we're going to get into a lot more depth very quickly here. So don't leave quite yet. We're getting there. But anyway, you go to your web browser and you type rule11.tech. What happens? When you type this in, the browser goes down to the operating system and says to the local host, all right, I need to convert this rule11.tech into a reachable address. In this case, it's going to be an IP address. Not that I can write today, but there you go. I usually can't. So we're going to assume that this is the server which we're trying to get to. This is where we're trying to get to the service. So what's going to happen is, given there are no preloaded caches, everything has just been turned on, what's going to happen here is the operating system on the local host is going to go to the recursive server, and you'll find out why it's called a recursive server in just a minute. And it's going to ask the recursive server, hey, how do I get to rule11.tech? What do I do here? Now, the local host is configured with a recursive server address to use. That is part of its configuration. Usually you would get this but from your service provider, from DHCP, or some other way, manual configuration on the host itself to know what recursive server to go to. So the recursive server starts on the right side of the domain, which in this case is .tech, and it moves to the left. So the first thing the recursive server needs to do is say, where is .tech? Well, where does it get this information from? Well, it reaches out to what is called a root server. Now, there are 13 root services in the world. There are not 13 root servers. We'll talk more about that in just a second. There are 13 root services in the world. That is not the same thing as root servers. There are thousands of root servers, but there are 13 services. Originally, when the DNS system was started, there were 13 root servers. There were actually 14, and you'll notice that one of them is missing in here. If you look for it, you'll find it. There's a missing root server. But anyway, that root server was kind of taken down. So anyway, what happens here is that there are each of these root servers multiplied and became more than one root server, and this address here that you use to reach that became what's called an anycast address. So what happens here is the recursive server is going to find one of these or ask one of these root services, how can I find out about .tech? Who do I ask about .tech? Now again, each root server is not a single root server. You can explore this in rootservers.org. I put the URL down here. I believe it's also in that extra document that you can download and play around with it. But if you look up here, you'll say, okay, I'm going to look at the root services in Frankfurt, or the root servers in Frankfurt. If I click on Frankfurt at rootservers.org, I get this kind of a map. And this tells me that there are one instance of D, 3 instances of J, 1 instance of K, 1 instance of C, 1 instance of I, 2 instances of F, 1 of H, 1 of A, and 1 of E. So there are instances, that which means there is more than one server necessarily in there. In fact, there can be more than one site. If I click on this J up here, it pops up a little screen that says there are 2 sites. Now, each of these sites will have at least one server. Could have up to 5 or 10 servers. So the J root service has at least 4 servers or 6 servers just in Frankfurt. And whenever you try to reach out to the J root service as a recursive server, you're going to reach and get in contact with one of these servers. Now, which one? This really depends on something called anycast. So each root service is reachable via one IP address. There are 13 IP addresses. So what happens here is the root server makes copies of itself through a zone transfer to multiple root servers all over the world, multiple copies. Like we just saw, there's at least 6 J server instances just in Frankfurt alone. So when this host reaches out to a recursive server and the recursive server tries to reach that IP address for one of those 13 services, it's 13 copies of that, one of those 13 IP addresses, it's going to be routed to the closest copy of the root server. And again, this is called anycast. So there are thousands and thousands of servers on the internet. In fact, a lot of the traffic on the global internet today is handled via anycast. People like Fastly and other CDN providers, Akamai, Fastly, and who else? Cloudflare will actually they'll convert what would normally be unicast addresses on a single server, and they'll convert them into anycast addresses by placing the content in many different places. So this is anycast in the global internet. So let's see. So I can see this by using traceroute. So 198.41.04, let's back up a second and I'll see what that was. That is a root server. It's run by VeriSign Inc. And we'll talk more about the organizations that run these in a bit when we get to DNS ecosystem, which is the next section of this presentation. But let's look at this address and see if we can figure out how to see this Anycast. So if I trace route to 198.4104 from Bangalore, India, I will find that it ends up in Tokyo, and then it stars out. If I look from central Madrid, South Africa, it ends up in, I don't know where lon3verizon.net is, but that's someplace there. Richmond, Australia, lon3 Verizon, VeriSign. I think that's VeriSign. I didn't really look those up. But if I'm from France, I end up in New York City. And if I'm Virginia, then I just end up staying in Virginia. So you can see that this one address ends up in different physical locations, different geographical locations, or reaches servers in different geographical locations. Now, these are also different topological locations on the internet. And you have to think about, when you think about IP addresses in the internet, you have to think about topological locations rather than geographical locations. You may have seen, like on some detective show where they, oh my gosh, I found the IP address and this person is from Miami and we're in Chicago, and look, their IP address is from Miami, so that must be the right person. That's all balderdash. It doesn't work. IP addresses are topological. And you'll pick up a new IP address when you move from one place to another. All right, so now let's continue with our operation of DNS. The root server is going to respond to the recursive with the address of a TLD. So what happened first was the localhost asked recursive server, where is this address? Where's rule11.tech? What happens here is the recursive server reads the address from the right to the left, says, where's .tech to the root? The root is going to respond not with an IP address, but with an IP address for a TLD. It's not going to respond with the service IP address, just with the IP address for what's called a top-level domain server. Now, this TLD server doesn't know where the service is located either. This is not what it does for a living. What's going to happen is it's going to say, I'm looking for an authoritative server that's going to give you the information about where this server physically is. So again, what I'm going to see is I'm going to see localhost, recursive server to root. Root responds with the TLD. Recursive asks the TLD. TLD responds with the address of the authoritative server. I haven't even gotten to the authoritative server yet. So next, I'm going to have the recursive go down here and ask the authoritative server, and that's going to return an IP address for where this service lives. And then the recursive server is going to send that information back to the local host. Now, this recursive server is not only going to send the answer back, it's going to cache the answer. It's going to stick the answer in a little thing and hang on to it. Yes, you will be able to listen to the recording after. Sorry, I went back and looked. So when I say an IP address is topological, do I mean that you're pulling an IP from that service's subnet topology, which could span a wide geographic area? Yes, but it's also, I'll actually get into topology a little bit later. I think I have a slide in here where I have two islands connected, and I'll talk about the difference between topological reach. Maybe I don't, maybe it's in a different class I'm thinking about, but actually I'll just show you real fast because I can whiteboard it. Let's say that you have a little island here, and on this island you have a house, and in the house you have a user. Then you have some island over here. Now down the middle of this island is some mountains, and you have a house, and you have a house, okay? And this house, there's no cabling over this particular mountain range. You have to go up to a satellite and back down to reach between these houses. However, there is a cable across the ocean floor between these two islands. Well, topologically, it doesn't matter what the physical or geographical distance is between these two houses. What matters is topologically, this is one hop. Topologically, these two houses, or geographically, these two houses could be a mile apart. But because of this mountain range between them and because there's no connectivity directly via fiber, it's actually a longer topological reach. So you'll find that your topological distance does not match your geographical distance. So that's why I use the two separately, because people tend to think that if you have two IP addresses, both of these could live within a single /16, for instance, and this could be in a different /16, but this part of this /16 might be closer to this part of this /16 than it is to the other part within the same /16. So that's why I use those quite specific terms of topological and geographical distance. So anyway, the recursive server is going to cache this. And all that means is it stores it in a local database for future use. The local host is also going to cache this in its own local cache. So it's going to be 2 copies of this. How long does this cache survive? Within each DNS response, there is what's called a time to live, or a TTL. This is usually spaced out in minutes or hours or days or something like that. And the recursive server is going to hang on to that information for the TTL, for as long as the TTL tells it to. Now note that the TTL is not fixed in stone. It is not written in stone. TTLs are, in DNS land, they are suggestions. The recursive server or the local host can, at any point in time, clear their cache and force all the cache entries to be rebuilt by doing queries. Of course, the point of all this caching is that the next time the local host wants to find that same IP address, it doesn't need to go out to the recursive. It has it locally. Now, experiments have been done showing that really caching doesn't necessarily reduce the load on the global internet so much as you might think. Drank a cup of water and that water kind of like went down the wrong place. So there you go. Your instructor is choking to death on water. No, just kidding. All right. So this caching, again, remember that these TTLs are really suggestions. They aren't hard fixed. You can go in on your host and clear your cache if you want to. Okay. So you can see this entire process using something called the Domain Internet Groper, or DIG. And you can use DIG as it's a part of the bind tools. I give you the URL here. There's some examples of using DIG in that document if you want to go through and play with DIG a little bit. DIG, by the way, only runs on Linux boxes or Unix boxes. You have to be in a Linux, but it does work, by the way, on Windows subsystem for Linux and on Mac OS boxes because they're Linux based. So it's not really saying that it's Linux only isn't that much of a problem if you use Windows subsystem for Linux or Mac OS. But anyway, it's only on Linux type operating systems. But anyway, you can get it here, and you can trace the entire thing using DIG. So you use this DIG, and it gives you all of this information. And of course, there's drill is an alternative. So for instance, if I dig for rule11.tech against the server 9.9.9.9, quad 9, and I often use quad 9 in my presentations, but there's no particular reason. I could use my local or I could use any other, but I do try to find a recursive or a route to come off of. Anyway, so if I use dig against 9999 with the plus trace, which tells it go through everything. So what happens when I do a plus trace on dig is that normally my host is going to query a recursive server. What I'm going to do when I do plus trace is I'm going to turn my host into a recursive server. So the host itself will take all the same steps that a recursive server normally would. So I can see the entire DNS query process, which is very, very helpful when I'm troubleshooting various kinds of DNS problems. So my host actually goes out and says, I am going to look at the root servers. So all of this section here is the root servers. And you can see that then I go through, once I've gotten my root server, my root and TLD, here's my TLD section. Here's my root server section, here's my TLD section, here's my auth server section, and this gives me all the way through. So these are my 4 queries that I'm sending to get to the IP address that's going to allow me to get to rule11.tech. So you can actually see each stage of the query using dig. And this is a very shortened, I've clipped a lot of the output out of dig by doing this in this particular slide. Again, in the document, I talk about how to use dig a little bit, and you can go through and play with it yourself and figure out how to do it. Okay, so someone asked, okay, so a couple of things came up in the comments here. Let's see. First of all, was a do-it-yourself person hard codes the DNS resolutions into etc. host for speed. Yes, you can do that. There's actually etc. host that will allow you to basically permanently cache certain entrance stuff. Dig does run on Windows. It used to. I think they stopped supporting it. The last time I looked on the website, they stopped supporting it. So I don't think they do. I don't think they do. There may be somebody else who's building binaries for Dig, but what would the consequences be if all or some of the DNS root servers got compromised? Well, you would get bad responses. And we'll actually talk about DNSSEC a little bit, which can be a counter to that in a later slide. But yeah, that's a problem. And so what a lot of servers will do is they'll query 5 or 6 root servers, and they'll see if they get the same answer, or they'll count on DNSSEC to do this. Now, one thing about loading a website is that when you load a website, it doesn't just do one DNS query to get to that website. It can do hundreds. This is one of the worst, which is dictionary.com. But you'll find this on most sites, except very clean sites. I don't think rule11.tech does much other than maybe Google for Google Fonts, but I don't have a lot of trackers or anything. But a lot of these sites have all these tracking pixels and all this other stuff that they do. So for instance, dictionary.com will do a CNAME. We'll talk about CNAMEs in a little bit. And then you'll see it goes to dictionary.co, not dictionary.com. And of course, they're using Fastly for a CDN. So you see them do a map for Fastly. They do some checking to Fastly. They do CETO parking. They do ads through PubMatic. They do Google tagging services. They do ads through Amazon. More PubMatic, more tag services, Google Analytics, and more Amazon ad services, and et cetera, et cetera. So you can see all of these places that it's querying to find information. Now, this is not uncommon with websites. It just depends. Dictionary.com is, like I said, one of the worst. There's like hundreds and hundreds on dictionary.com, which is why I use it as an example. Almost all websites will do this kind of thing where they're querying other sites for information. Okay, so let's talk about DNS aliases a little bit, because a DNS name is not just necessarily a service, but it's also potentially an alias. And an alias is, what an alias is just like a DBA, doing business as, or a nickname in some sense. So let's talk about rule11.tech for a second, because rule11.tech actually, well, for a long time was an alias. It still kind of is a CNAME. So I think I have an example in just a second. But anyway, what happens is when the local host asks the recursive says, go to the root. The root says, go to this TLD for .tech. The TLD says, go to this auth. And the auth answers, oh, by the way, rule11.tech is a CNAME. I don't have the IP address under that particular name. What you need to do is you need to ask about my old hosting service, which was wpengine.com. So when you get your response back, the recursive is going to say, oh, this is a CNAME. Now I have to go ask about wpengine.com. So what I'm going to do is I'm going to go back to the root, ask about .com, go back to the TLD, ask about WP Engine, go back to the auth, find the right address, and then when the host sends IP packets to the service, to the server on which the service resides or is running, then this service or this server will automatically proxy that and know what to do with the rule11.tech queries and send it to the right service sitting here on this server. So this is quite common in these situations to have a CNAME or an alias. So again, let's see. So One place where this is often used, and I don't know if I have it here. Yeah, I don't have it in my slides, is, for instance, you see rule11.tech right here. Well, rule11.tech is actually a CNAME for www.rule11.tech. So when you do a query for rule11.tech, the recursive is going to get a CNAME back and say, ask for www. When you get www, it's going to go straight back to the auth server, which is going to give it the correct IP address. So you will often find that CNAMEs are used to carry services directly to a server rather than to a particular different server or something like that. Now, what about negative responses? What if things don't exist? What if I ask for something that does not exist? In this case, what's going to happen is I'm going to get one of two kinds of responses. So assume that a local host asks for www.banana.example to the recursive server. The recursive server goes through the TLD and everything else and gets down to the authoritative. There are two possibilities here. And actually, these possibilities exist at the TLD, at the root server, all the way up through the chain. The first is what's called a no record. So this is or a server not found. You'll often hear this called a server not found or an SNF record. And there's no actual record here. What it means is that banana.example exists, but www.banana.example does not exist. So that's going to give you a no record response. Now, this is not a record at all in DNS. This is a response based on the server. There's no TTL. There's nothing else. This is just a cache negative response so that the recursive server knows this server within this domain does not exist. Now, the other option is what's called an NX domain. Now, here, this means that banana.example itself does not exist. .example might exist, but banana does not. Or even .example does not exist. It just depends on where you are in the tree and what doesn't exist. This NX domain is an actual record return that can be cached by the recursive server, and this has a TTL. Why am I telling you about these caches? Because these caches are what you have a problem with when you go to change the IP address attached to a given service. So let's say that you own a particular DNS name and you go out and you take the address off of it. Say that I take rule11.tech and I say I'm going to change my server. So I go in and I take the IP address out of the record. So there's no A record, there's no IP address, there's no service address of any kind associated with rule11.tech. Now what's going to happen is the local host is going to ask the recursive server, what about rule11.tech? It's going to ask the auth server or wherever it asks, and it's going to get an NX domain. So when that happens, it's going to cache that NX domain for as long as the TTL is. So now if I go back and I put an IP address back in here, I go back to rule11.tech, and I put an IP address in there, what's going to happen is that even though I've now queried for it, the next time the localhost queries for it, it's going to still hit that cached NX domain record or that no record that's been cached by the recursive server. In which case, that means it takes up to 24 hours for that TTL, that cached negative response to time out and for you to be able to reach rule11.tech again. You should always put in that new address in before you take the old address out type of thing. So there's ways around this, but it's something you should be aware of, that when you go to a DNS provider and you say, I'm going to change my IP address, they say it can take up to 24 hours. That's more than likely because of negative caching. So again, how long are these negative caches kept? For server not found, there's no TTL in the record or in the response. So it's just based on some local configuration. For NX domain, there is a TTL and it's kept for that long. So again, the negative cache is often the problem when you are changing a domain name. So let's see. All right. Now let's assume that we have the IP address of this service and we would like to start a session with it. But when we do that session beginning, we notice that it only accepts encrypted connections, what are called TLS or SSL connections, secure socket layer or transport layer securities connections. So now, if I'm going to connect to this service in a secure way, say it's my bank or anything else on the internet, how can I figure out, because I need the service's key, I need some way to encrypt data so that the service knows how to unencrypt the data so it can read the data. So I need a key for this service. Particularly, I need a public part of a public private key pair. So I need to find this. There are actually DNS records for this, which is why I say that DNS is not always just IP addresses. It's any sort of a service or piece of information out there. So what's going to happen here is I will go to my recursive server. My recursive server will go to the auth, and the auth will give me a list of servers which have the key, the public key for this particular server. So these are called CAA records, certificate authority records. And so you can go through that certificate authority list, which is then returned through the recursive server back to the host. The host can now go to the CAA server, grab the certificate for the service or the server sitting out here that I want to talk to. I can use that to encrypt my data down and build a TLS or an SSL session to the server. Now, we wouldn't use the public-private key pair to actually do encryption, but just to carry a secret key that we would then use to encrypt the data. So again, that's maybe a little bit craziness in terms of encryption, but that's pretty much how it works. Now let's talk about something else in the DNS land, which is, all right, just checking for questions, which is whois. Now, unfortunately, or fortunately, depending on your perspective, whois has really been backed down. The amount of data available in whois has really been backed down because of privacy concerns. So if you go to places and you look at whois records that have the full information, you'll get things like people's email addresses, physical addresses, you'll get IP addresses, you'll get cities and all sorts of stuff out of whois. A lot of registrars are taking that information out of whois, so you won't get as much information out of it. But what you still tend to get out of whois, you can go to IANA or any other whois services. I think there's a few more listed in the document that accompanies the course, or you can actually just go on the internet and look up whois services. Just watch, because when you do like a search for whois services, what you're generally going to get is you're going to get domain name service registrars that sell domain names, and they're using the whois service that they've provided as a way to try to sell you domain names. So be a little bit careful about using whois services on the internet. I tend to use IANAs because IANA manages all the domain names, and they're not trying to sell me anything for the most part. So they're not collecting my information and blah, blah, blah. So you can go to whois, do a query. You'll find that this is the registrar, which is namecheap.com. You'll find out when it was registered, when the last time it was updated, when it expires. Most people have their domain names on auto renewal and stuff like that. The registrar, this just means that namecheap.com is a company registered or is incorporated in Panama. And then you'll see that you can do the two name servers that you should use, the authoritative servers. And you'll see down here a phone number. These are very important, this information right here, because this gives you an email address, a phone number, and a complaint form if there's an address in this domain that's being abused. So if, like, for instance, if you get a spam email from rule11.tech, you never should, because it's just my website and I never send email from that address, you can forward that email to abuse.namecheap.net, and they'll analyze it and figure out who the user is and contact the actual owner of the domain and figure out what's going on if there's a lot of reports. So this information and who is very important and useful. All right, so let's talk a bit about DNS security. We had a question on this earlier about what would the consequences be if all of the DNS servers were somehow compromised, or one of them were compromised, or whatever. So let's talk about DNS security just a little bit before we jump into a break. The first problem we run into in DNS is what's called cache poisoning. So if a local host sends a request to a recursive server, the recursive server jumps through the root and TLD and gets to the authoritative. The authoritative responds with a correct response. An attacker who has access to anything in this path, in terms of being able to see packets and DNS responses and stuff like that, can, a few moments after the authoritative server responds, send a poisoned response. Now, because the recursive server doesn't know the difference between the correct and incorrect response, it will simply accept the later response as the correct response. As long as you can see what the authoritative server is doing, and you have access to the recursive server to send responses to the recursive server, it's very easy to cache poison like this. It's a very common, easy problem to cause. So why would we do this cache poisoning? What would we be doing? So what we would do is that rather than allowing the local host to send its traffic to the real service, what the attacker wants the local host to do is to connect to the attacker's server. So now what's going to happen is, remember I told you can build a TLS or a secure socket layer secure session, encrypted session. What will happen is the local host will go down here to the attacker server, build an encrypted session with the attacker server. The attacker server on the backside can build an encrypted session with the real service and pull the data from the real service and push it back to the local host. The local host in this case is man in the middle. The man is being man in the middle, and it does not know that there is an attacker server reading all of its data. So this is one possible attack that you can get into from cache poisoning. So how would you solve this? Well, one way to solve this is what's called DNSSEC. So what DNSSEC does is it actually allows you to sign your DNS records. And the way these are signed is the registry will sign .com, and then it will also sign that this domain owner owns example.com. Now the domain name or the domain owner for example.com will then sign banana.example.com, and then the subdomain owner can actually sign for the service owner for www. So you have this onion layer or onion peel way of seeing what's been signed. So when you check for www, you're going to be told, yes, you need to go to banana and you need to find the correct record for that. And it's going to give you a signature or a key that you can use to validate the signature on the www portion. And then if you want to validate banana, you go to example, it's going to give you a key. It's going to allow you to validate the banana portion of the domain name. And if you want to validate the example, you go to the registry.com and you can find a key that will allow you to validate that example is the correct answer. So now if you do this, if you see this, what happens is that when the local host sends the query out and the poison response comes back, the host can say, no, DNSSEC signature does not match. I'm going to reject this poisoned response. The recursive server can do that as well. So this blocks the attacker from poisoning the cache. So DNSSEC is actually a very big deal in the world of DNS security. And not all domains are DNSSEC enabled, just some of them. So that is some of them. Can I please explain again the negative response to no data? Let's do that real fast and then we'll take a break. Okay, so if the host does a query from banana.example to the recursive server, the recursive server takes that and goes through the TLD root, blah, 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 gets to the authoritative server. And the authoritative server says banana.example exists, but not the www service. So that means there is no record. It doesn't mean that the domain doesn't exist, just that there is no record for this service attached to that domain. In that case, the authoritative server is going to send what's called a no record or a service not found or a server not found. Sometimes you'll hear it abbreviated as an SNF reply. This is not a record of any kind. It's not an official specified DNS response or whatever it is. It's just a response that the authoritative server can give you for that particular domain. Okay, so next we're going to talk about DOT and DOH, but it's 251. So what we're going to do is we are going to jump over here, stop sharing, and I will blank. I'll cut my video and we'll come back at just at 1 after. We'll try to make it 10 minutes because the slide is a 10-minute break slide. And I don't want to make the slide wrong, so we'll make the slide right. Okay, we'll see you in 10 minutes. 15, 14, 13, 12, 11, 10. And we have liftoff again. Look at that. So I don't know. All right, let's see. So we've talked a bit about DNS security a little bit. Let's talk about DOT, DNS, DOH, and just a few more slides on security. And by the way, just so you know, this is a completely different formatting of slides and stuff. So I'm actually not certain. How many slides do I have? Let's see, I have 101 slides for this. And in the first hour, we made it through 27. So I guess that's pretty good because it's supposed to be 4 hours total. So let's talk about DOT and DOH. I will try to slow down a little bit. I know that I talk really, really fast, and people have a hard time keeping up with my rampant and slightly disorganized rabbit trailing and stuff like that. But that's okay. All right, let me share my screen. I will share slideshow. There it is. Everything still seems to be working. All right. So let's talk about DNS over TLS and DNS over HTTPS. This is not TCP, this is TLS. So these are both forms of encryption for DNS queries. So first of all, what is the problem we are trying to solve by encrypting DNS queries? Now, if your host, if your local host, operating system, Windows, Mac, Linux, whatever it is, Android, iOS, doesn't matter, all of those things, when they send a query to the recursive server, your access provider and anyone within your access provider or sitting in the coffee shop with you over that Wi-Fi link that you always use when you're sitting there drinking some coffee and messing around with your bank account can see the contents of your DNS queries unless you're on an encrypted session. But remember that in order to encrypt the session, what do I need to do? I need to go to a different server, follow the CAA record, and get the CAA, get the public key for the server I want to talk to in order to build that encrypted session, right? So my DNS queries are by and large going to be unencrypted, running over whatever link I'm running on. So my access provider has access to those. The dude sitting next to me who's war driving over the Wi-Fi access point or whatever is going to have access to my DNS queries. That may not sound like it's a big deal, but when I worked for a DNS provider, we discovered lots of things about people and companies just by querying or just by looking at their DNS queries. We could tell all sorts of weird stuff. Which company was thinking about buying another company, when companies were thinking about merging, all sorts of stuff from the DNS system. Because we had root servers, and we could look at the root servers and see what was going on with queries. So people can tell a lot about what you're trying to get done. If you do a query for a bank, they can guess that you bank at that bank because you're trying to get to that website, et cetera, et cetera. So this is the problem that DOT and DOH are trying to solve. So the way that DOT works is when your browser sends a domain name that it wants to get to down to the IP stack on your operating system, it is going to encapsulate that in a TLS encrypted session to the recursive server. Because it's encrypted from the host all the way to the recursive server, the access provider and this war driver sitting here on your Wi-Fi access point cannot see the data, cannot see the DNS data. Now this works pretty well, but the problem with it is for some particular operating systems like iOS and Chrome and things like that, you don't really have an operating system with a stack that's separate. So for those operating systems, and what is most normally done now is what's called DNS over HTTPS. So what will happen is that your DNS server, your host, will actually, the browser itself will do the query to the recursive server using an HTTPS connection. So the outside users can see that you're querying to get to, that you're DNS querying to get to the DNS server itself, to the recursive server. If they cannot see, or well, if you have it programmed in or configured into your operating system, not even that, but all they'll see is encrypted traffic going to the recursive server and encrypted traffic returning. So this blocks all those people that are in the middle, like access providers, war drivers, attackers, that type of thing, from seeing your DNS query chains, which gives you a a better way of doing things. So, okay, somebody asked here, they installed the drill command, brew install LDNS. What is the benefit of using that over dig, if any? It's just a fork on dig from what I remember. It's just a different version. And I think that drill still supports Windows, and I don't think that ISC still supports Windows for dig. So I don't know that there's any massive advantage or disadvantage. It's just a different open source code base. Okay, so this is what DOH does and what DOT does. So there are, however, positive and negative aspects of DNS over TTLS and DNS over HTTPS. It's not all fun and games. Positive aspects are what we just talked about. Removes visibility from transit last mile providers and even across Wi-Fi and cell links, things like that. So it does remove visibility. It complements DNSSEC in that DNSSEC is going to validate that the record that you've received is the correct record. DOT and DOH are going to make sure that the record being transmitted that you're receiving is actually being received from the recursive server you are connected to. Another way to cache poison is to poison your local host cache by sending the response directly to the local host rather than even to the recursive server. Now, there are a lot of negative aspects to DOT and DOH. First of all, if you operate a network and all of your users use DOT and DOH, you lose visibility to their DNS queries. So a lot of times security systems will check, and logging systems will watch the DNS queries coming from hosts to look for things that people shouldn't be going to on work time. If you use DNS or DOT and DOH, you lose that visibility. A second thing is that the browser selects the DNS server rather than the OS. So if your host is assigned an IP address and a recursive server via DHCP or manual configuration, if your browser is doing DOH, then whatever is set in the host is not what's used. What's used is what's in the browser. So you have to go find that other place for setting the recursive server and make sure it's set the way you want it to. Now, one game that's being played here is that the content providers are setting up DOH servers like Google and Microsoft and blah, blah, blah. And they are selecting, if you use Edge, it goes to Microsoft's DNS server. If you use Google Chrome, it goes to Google's DNS server. So this gives them more information because now they can see your DNS queries in full, where before they might not have been able to do that because you would be querying some recursive server that's paid for by your local access provider or something like that. So that's why I say it can hand more data to the content provider, and it can actually play a role in the centralization of the internet. There are really only 3 or 4 browsers in the entire world. If those 3 or 4 browsers, each of those browser manufacturers select their own DOH servers, then what happens is all the other DNS servers in the internet kind of lose their mojo. They don't get all the DNS queries. And so that kind of contributes to the centralization of the internet. Now, another thing I want to talk about real fast is this idea of leakage of DNS information. I'm showing here through a VPN. There's another place that DNS information leaks as well that I'll talk about real fast on this slide. So if you're in a VPN, if you're using a VPN, part of the reason you're probably using a VPN is to for instance, fake out the country you're in. And I know that that's not legal in some places and stuff like that, but people have valid reasons for doing this, where they will say, all right, I'm in Australia and I want to watch something in the US. So I use a VPN where this VPN server is in the US. So it'll look like I'm in the US or whatever the case might happen to be. Well, what happens though is if I query to a DNS server in Australia, then it's pretty obvious that I'm not in the United States, I'm in Australia, or whatever the case might happen to be. So this is just one form of leakage you can get into with DNS. You can leak where you are physically, even though you're on a VPN, because your DNS queries don't necessarily go through the VPN. So what some VPN service providers do is they provide their own DNS servers that you query. So when you set up the VPN connection, it'll change your local DNS query, your local DNS recursive server to be configured for the VPN provider's recursive server. Now, of course, again, if you're using DOH, unless they've gone in and changed it in the browser as well as the operating system, you're still going to be leaking this data. Now, another place that you get into leaking is when you do a query to a recursive and it queries the root. There are a lot of implementations of DNS recursive servers that will send the entire query to the root. So for instance, if you're doing www.rule11, did that all wrong, .tech, it will send the entire query to the root. So the root operator, whoever owns that server, has access to that server, doesn't know that you're just looking for .tech. It knows for what service and what domain you're looking for. In reality, the root server doesn't need to know all of that. So it's kind of a privacy violation. So another thing that this happens with is that if you have a corporate network computer that is sitting behind a firewall and it does a DNS query and it queries for an internal server name to the recursive, anybody sitting between you and the recursive itself now understands how you name your servers internally. So there are lots of places where DNS can leak information that you need to be careful of. The DOH, DOT, DNSSEC, none of that solves these leaks of information out of DNS. You have to be careful about your configurations and about query minimization and other things to stop these leaks. All right, so now let's talk about the DNS ecosystem. So what I mean by the DNS ecosystem is who pays who and who pays for what. It's very important when you're dealing with global internet to understand who pays who and who pays for what, because it makes a big difference in what phone number you're going to call when you have a problem. And it's also going to be very indicative. Sometimes there just isn't a phone call you can make because the person that's causing the problem is not someone that you have a financial arrangement with or a contract of any kind. So let's begin here. We have 4 kinds of servers we've talked about: root servers, TLD servers, authoritative servers, and recursive servers. Who pays for these? The costs associated with these are hardware, software, operations, somebody's got to program them, somebody's got to upgrade them, etc. Maintenance, somebody has to replace the server when it goes down, whatever. Bandwidth, all of these servers, I mean, top-level domain and root servers consume lots and lots, and actually recursives do as well, consume a lot of bandwidth. Somebody has to pay for that bandwidth. And then, of course, there's development. DNS is always being added to. Who is building the standards? Who's paying to build those standards? So let's start at the recursive servers. Who pays for these? Most of the time, recursive servers are run by access providers, your last mile provider. So let's say that you have an account with ATMC and you are buying internet service from ATMC. I actually don't know that ATMC is a service provider that has a DNS service, but I know Viasat does, I know Spectrum does, and Verizon does. So these access providers will bundle the cost of paying for a recursive service into your monthly subscription fee or your access cost to get to the internet. So that is one way that these recursive servers are paid for. Cloud providers like AWS and Google will often provide recursive servers like Google Public and AWS Public DNS servers. First of all, to gather information, to be honest, they want to gather as much information on users as they can. Second of all, as part of their cloud services. So if you're running a workload in AWS or Azure and you want to be able to do something with that service, you might need to get to a DNS server. Well, rather than having that traffic jump out of Azure Cloud or AWS Cloud or Google Cloud or Linode or whatever it is, they'll run their own DNS servers that you can run to locally that give you the ability to add lots of subdomains and stuff for internal operations. There are also security and edge providers. We'll talk about these more in later sections, like OpenDNS provides a filtered version of DNS. Quad9 is another one that provides a secure version of DNS. Akamai provides protected DNS services, so you can transfer your zone to Akamai and they'll let you run your DNS within the Akamai network, which allows you to have a protected domain or protected zone files and stuff like that, and also accelerates type thing. Cloudflare does the same sort of a thing where you can accelerate your DNS service by pushing stuff to the recursive servers running inside Cloudflare. So these are business models that work for recursive servers. So I said, Chrome seems to have secure DNS, which I think is DOT, enabled by default with a value with your current service provider. So Chrome, I think, has two settings, one for DOH and one for DOT. Most of the time, if you go into Chrome and you see secure DNS, that's going to mean DOH rather than DNS over HTTPS rather than DNS over TLS. And then AW said that there's a weird feedback when I talk. If other people are hearing that, please let me know. I can try to play with my mic a little bit and see. Sometimes I get a little bit too close to my mic and it overwhelms the mic and blah, blah, blah. So that's something that's there. All right. So these are my recursive servers. Now, the recursive server first, when it does a resolution, is going to ask a root server. So who owns root servers? And why? I told you before, root servers, there's thousands of them. It seems like there would be a lot, it would cost a lot of money for VeriSign, for instance, to go run all of these root servers. So it does. And what they do is, first of all, some of these root servers will run in clouds as a service on AWS or Linode or Google Cloud or whatever, and they'll have these instances that are out there that aren't actually servers they're maintaining. Or they'll buy root service, they'll actually go out to like Equinix and co-locate on a server, a virtual server or something in an Equinix data center to get the root server up and running in more places. Oh, someone asked about the Sony and Quad9 legal situation. I don't know a lot about it right now, what's going on. I've just heard a little bit about it myself. I'm gonna have to go do some investigation on that because I haven't really spent a lot of time on it. Maybe over the next break, I'll try to poke at it and see if I can understand what's going on there. Okay, so yeah, it does cost a lot of money for these companies to run these root servers. So how do they get their money? So VeriSign, for instance, is a for-profit company that what they do is they make money by managing .com and .net and selling services to other companies, DNS services to other companies. So they make their money this way, and they just consider running the A and J root servers to be a cost of doing business. If those root servers didn't exist, their business as the manager for .com contracted manager for .com would go away. So they just consider it part of their job to do that. Now, there are some of these like University of Southern California, ISI, University of Maryland, NASA Ames, NetNod, and RIPE NCC, and ICANN, and WIDE Project that are nonprofits that are just funded by governments or by donors or large companies will say, okay, USC, ISI runs B-Root server and they need X amount of money every year, and they'll just go around hand in hat and say, we need money for this. It just comes out of their operational donations and stuff like that. NASA Ames, I said that wrong. NASA Ames is supported by the US government. They just keep their servers up as part of their research program. The eRoot servers are up as part of their research program. ISC is a nonprofit which sells bind tools and support for bind tools, and they support their FRoot operations out of that financial situation there. So ICANN makes their money by selling the top level domains, and then they use some of that money to support the LRoot servers. So everybody supports their servers a little bit differently. So who pays for TLD servers? So top level domain servers are usually paid for by registries that own the top level domain. So I believe, I don't remember exactly who owns .com. It's under contract via VeriSign to VeriSign. And what happens here again is VeriSign gets a certain amount of money. We'll talk a little bit about their business model a little bit here in just a minute, so I won't dive into it in a lot of detail. But like Donuts owns tons and tons of TLDs. Actually, they own 307 at last count, top level domains like .academy, .agency, .bargains. Anytime you use one of those domains, you're paying a little bit more for that. And that money goes to Donuts, and they use that money in part to support their TLD servers. Automatic is WordPress. So anything .wordpress, there's a TLD out there for a TLD server for that. Newstar is another one kind of like Donuts. Then you have Alexa. So Alexa manages the domains and subdomains for the Alexa line of services, their home automation stuff like that. So again, this comes out of Amazon's profit. So this is how TLD servers are paid for. So who owns authoritative servers? Authoritative servers are typically owned by companies that sell web hosting and or domain names. So for instance, I use Namecheap. Namecheap has authoritative servers. Part of the service I get when I pay for my Namecheap subscription is they manage those authoritative servers. If you go to web.com, SiteGround, GoDaddy, Network Solutions, and now Network Solutions used to only sell domain names, but now they do sell web hosting. So if you do web hosting through any of these people, they will often have their own authoritative servers that need to be programmed to make DNS work. So now let's talk about where domains come from. So this is kind of the way money is made in this market. And again, the next slide I have is on VeriSign and their specific business model. So IANA creates top-level domains. When they do this, they delegate their authority to ICANN. ICANN sells the top-level domains at an auction to various TLD owners. So every couple of years, ICANN will say, all right, we're going to release the .foo domain or whatever it is, .banana domain or whatever it is. And interested parties will go to ICANN and say, we would like to have a top-level domain that says blah, whatever it is. And then ICANN will react to that, do some adjudication, do some legal stuff, and they may eventually sell that TLD at auction. The TLD owner invests in that TLD in order to make money off the TLD in some way. So for instance, Amazon sells their Alexa product line, and they actually make money by people buying and subscribing to Alexa services. So they pay for that TLD, or they bought that TLD in order to make those services possible, in a sense. So much the same way. What will happen is the TLD owner will often then sign a contract with a registrar like Namecheap, or like VeriSign really is the big one, because they do .com and etc. And there are others. I think Donuts also does this, and there are some others. But anyway, to manage the top level domain, that registrar will then sell individual subdomains of that top level domain to users to create DNS records, subdomains, etc., 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 that are then used to host websites and etc. So you can see this kind of chain of money. So when you pay money to register a domain name, some of that money goes to the registrar, some of it goes to the TLD owner. The TLD owner is paying back for buying the TLD at auction from ICANN, and that's how ICANN makes its money. So this is an example using VeriSign specifically. So the way VeriSign works is they have a contract for can't even write. That's so terrible. .com and .net. So .com and .net is contracted to VeriSign. So VeriSign, what they have is they have the cost of operating the A root, the J root, the cost of operating their TLD servers, and their authoritative servers for these two domains. They also subcontract, or they contract for other TLDs, but the two that are the big ones are .net and .com. So what they do is, by contract, VeriSign charges a fixed fee per domain. So they will charge $5, $7, or whatever it is for every .com that's registered in the entire world. If there's 2 million .coms registered in a year, they get $5 per .com, whatever it is. The scale here, I think I may have something here that talks about the scale in one of these slides coming up. So anyway, we'll talk more about that in a second. They also get contract operating fees from TLD holders and other operations. Like somebody like Bitly or something like that might go to somebody like VeriSign and say, since you're already deeply into the DNS business and you own these top level domain servers, you can make my service, whatever it is, URL shortening, it doesn't matter. There's a lot of different services that you can do in the DNS service faster. And therefore, I will pay for you to host my service, and then I'll charge my users for the service and use that money to bring money back to you. So this is a fixed fee per domain. Now, what a domain reseller does is they are going to take the market value of the domains and then the hosting fees and use that, the differential between that and the fixed fee per domain, to make their profit level. So if you go to say, I don't know, if you go to say Namecheap and you say, I want abc123.com, you're going to find somebody's already registered it and they want $5 million for you to buy it from them. So the transfer cost and the cost of operating that marketplace for domain names is a profit source for people like Namecheap and other like GoDaddy and Network Solutions. So they're going to take that money and use it to pay off the fixed domain fee per domain, and then they are going to use the rest to operate their business and do other things like that. So this is how VeriSign makes their money. Most of these DNS registrars make their money in a similar way. To give an idea of scale, 341.7 million domain names registered across all top-level domains. This is in fourth quarter of 2021. I did check to see if there was a later one when I built these slides, but anyway, I'm not sure that they've come out with the 2022 numbers yet, but you can always look at verisign.com for the more recent numbers. About 3.3 million new domain registered in the fourth quarter of 2021 by itself. 160 million .com registered totally, 127.4 million country code domains like .us, .cn, .to, all of those are country codes. .eu, et cetera, et cetera. Those are all country codes. And 24.7 million generic domain names registered. So if you're getting $5 per domain for .com, you're not doing too bad. So this is kind of the way the business works. All right. Now let's talk about email. I will tell you why I added this section. This didn't used to be in my How the Internet Really Works slides, but I added this section. I'll make sure there's no more questions on DNS before I move on. I added this section because about 4 or 5 years ago, I got a mortgage. Maybe it was more. I have a mortgage more recently than that, but at this particular time, I was getting a mortgage. And the person at the bank where I was getting my mortgage said, email me your filled out forms with your income levels and social security number and everything else, and a copy of your social security card and your W-2s from all your last 3 jobs, last 3 years, whatever, and just email them, scan them and email to me. And I said, no. And they said, well, my email system is secure. You don't need to worry about losing your data. And after picking myself up off the floor, realizing that people just don't know how email works. It doesn't matter if she is on a secure email system because her email system is only half of the email process. So let's talk about how email works. So from the sender side, I have what I would consider an MTA or a mail application like Outlook or something like that. And I am going to create an email. And this is going to be created in an email format. It's a standardized format. I'll get to it in a second here. Anyway, so you're going to be able to send that email via Simple Mail Transfer Protocol, SMTP, to your server. You don't send it to the receiver server. You send it to your server. Your server then does a DNS lookup for what's called an MX record in DNS and sends the email via the MX record to the receiver server. The receiver then logs into their server and grabs the email. Now, there are various ways this can happen, right? There is POP, which Post Office Protocol, which downloads the emails onto the receiver's local computer and then deletes them off the server, which saves space on the server, which is really cool. But it means that if I have 2 devices, like I have a tablet or something that I connect to the server with, once I've done POP, I pop the email off the server, I can't get to it again. So the other option is something called IMAP. And IMAP just synchronizes my local mailbox with the server's mailbox so that I have a local copy and a copy on the server. So I tend to prefer to use IMAP. I think just about everybody does use IMAP now rather than POP. POP v3 is kind of an older dying technology in my opinion. Now, there is another thing here where you're using webmail. Now, webmail, there is a web application running on the server. And when you compose the email, you're composing it on the server. So you're actually sending keystrokes to the server and you're composing it on the server. You're not actually using a local mail agent of any kind to do that. So in this case, you're counting on the link between your browser and the server being encrypted to protect your email. It's actually very easy to spoof email. Why? Because if the receiver's server is open, which it almost has to be for many senders to get to it, you can create a fake server, send email using the sender's domain name and address, and make it look like to the receiver that that email came from this server and this sender, even though it didn't. So any server can use SMTP to send email to any other mail server. The originating email address does not need to match the local sending server's domain name. Now, there is a technology here called DKIM, which makes this a lot harder. So what DKIM does is it uses a private key to encrypt the mail header and makes it where you can actually, as a receiver, go back, find the original mail header encrypted so it's not been modified, and make sure that the mail header contains the right information for the sender's domain name and etc. This stops some source spoofing. I say most in my notes here, but it's not really necessarily true, because what you can do is you can grab the DKIM off of another email and play replay attacks and stuff like this. So it does stop things, but most spammers today don't actually spoof the source address, or a lot of them don't. They just go ahead and use a real email address that's discardable, so they actually have a valid DKIM signature. Another thing that will happen here is the receiver will sometimes do a reverse lookup. Not always. They should be doing this, but they don't always. So what happens here is when the receiver receives an email, an SMTP connection from the sender, it will take the IP address of the origination and it will do a reverse lookup in DNS with something called I can't write, in-addra ARPA, and in-addra ARPA will return a DNS name based on the IP address. This is all described, by the way, in those notes that you can download. You can see how to look up in-addra ARPA addresses, and it will actually check to make sure that the sender's domain matches the IP address of the originator. This is all part of something called the Sender Policy Framework. So if you have Sender Policy Framework enabled, it's a lot harder to spoof source origins. Of course, again, most spam is being sent from email addresses that are valid. They might change it in the header to make it look like it's something different, but it's not the actual sending address. So all of this work stops some kinds of spam, but not all kinds of spam. So what if I am not receiving email or someone is not getting my emails? What you need to do in this case is you need to look at what are called blacklists. So there are all these different blacklists out there you can find. I think there's a list of them in the document. I'm not positive, but you can do research on this yourself. You can just do a search on any search engine and say, I'm looking for email blacklist or domain blacklist, domain reputation tools. If you do this, what you'll find is that you can go out and do a search, and you will find that you do a search for your IP address or for your domain name, and it's going to tell you who has you blocked. Now, in the case of rule11.tech, there's not even a mail server on rule11.tech. There's no reason for it to be blocked. But as far as email goes, but AdGuard Family, AdGuard Clean Browsing, Adult, Family, etc., all of these different services have built a reputation or decided the reputation of rule11.tech is a clean address. Now, this doesn't just apply to email. This also applies to websites and stuff like this. They actually do reputation across all these things. So if you're having problems sending emails to someone, you should always check these block sites, these blacklist sites, and see what the reputation of your domain is. That's the best place to start with these things. Okay, next section is we're going to talk about routing. Now, routing tends to be just a hair more technical than DNS does, and a bit more abstract, unfortunately. So I'll try to take my time going through this and help you understand what routing is. All right, what is an IP address? Oh, I even told this earlier. This is not how IP addresses work. These dudes, they're clueless. Okay? IP addresses are not tied to geographic or well, the IP address assigned to a particular host is not necessarily tied to the geographic address of the host. It's the topological address. So if you go back to my two islands example, you will find that um, the topology doesn't always match the geography. And furthermore, when you move your host from one geographic location to another, you're going to get a different IP address. So that's just the way things work. All right. Here is the same slide I hand drew before. Right. IP addresses are not permanent host identifiers, interface identifiers, or geographic location. An IP address is where the device connects in terms of the network's topology. Why do we do this? Because in order to control the state in the global internet, we must have aggregable addresses. We have to have addressing that we can aggregate at different points in the internet to reduce the control plane state, to make the internet actually work and converge. So if you want a network that scales, you have to aggregate. So now let's talk about routing. Packets don't have drivers. So if you think of a routed network as a road network, and these are my links, but they're also roads, I'm considering them roads, and then these are my routers. I can't put a packet on the wire, and there's nobody in the packet who's going to look at the road signs and say, go here. But these are actually much like a telephone switchboard. Something or someone has to figure out which destinations are reachable via which physical paths and make the right connections and carry stuff the right way. So these devices in the internet are called routers. Now we also call them switches. I call them routers, but that's okay. Routers talk to each other using what are called routing protocols. So a routing protocol is basically there to find loop-free paths through the network. BGP version 4 is the current routing protocol that runs the internet. BGP version 4 has various things that you kind of need to know about, or different terminology here that we need to deal with. First of all, we have what's called reachability information. Now, we normally call this a route, but a route is not a destination. A route is a destination with a path. So what we have is what's called a network layer reachability information, or just reachability information. This is a service, a host, or a network that's reachable via the internet. An NLRI or a reachable destination does not become a route until you add attributes to it. So things like an AS path or something like that. So a BGP router or a BGP process is called a BGP speaker. An autonomous system is a collection of networks or a network under the control of a single administrator. This is a little bit tricky because what we mean by a single administrator varies over time and in different situations. But generally speaking, the way we define an AS is that an autonomous system should look the same from all exit points. The policy should be contiguous or consistent across all entrance and exit points. So that's the way we kind of define an autonomous system. Peers are two BGP speakers who exchange routing information. Now, there's another meaning of the word peer that we will get into in just a few minutes, so keep that in the back of your head. And the best path is a loop-free path through the internet. And routing policy determines which loop-free path to choose. And I often like to say a real policy. What a real policy does is it takes you off the best path. It takes you on to a less than optimal path from the routing metric perspective. So there are three basic kinds of policy that I'm going to deal with in routing. If you're very interested in this topic of BGP policy, I have an entire 3-hour live webinar that I will be teaching sometime in the next year, doing nothing but dealing with BGP policy and understanding BGP policy in depth. So you might want to look for that if you're really interested in BGP policy. So the first policy that we deal with are what's called exit selection. From 65,002's perspective, what I want to do is I want to make sure that the traffic on this settlement free link remains equal in both directions. Why do I do that? Because if the traffic starts getting too heavy in one direction, one of these two providers is going to end up owing the other provider some amount of money. It becomes a settlement link in a lot of contracts. So another thing that you want to do if you are an AS 65002's perspective is you don't want to push traffic from AS 65002 down to an edge or an access provider to get to a peer, to get to another transit provider like AS 65001. So a lot of your exit selection here is done based on the type of business you're peering with, the type of provider you're peering with, the type of peering session that you have. And this is often done with something called local preference. But again, I'm not going to get into the depths of local pref and BGP policy in here because I have a separate session on it. Now, from AS 65002's perspective, again, if I'm dealing with entrance selection, I want to make sure that traffic enters my AS at the right place. What I want to do here is I want to again make sure that this settlement-free link remains settlement-free, and I want to make sure that any traffic that originates in AS 65005 comes directly to me rather than going through AS 65001. Why? Because this is a paid link and I pay money for that traffic to come to me that direction. On the other hand, if this is an upstream provider customer relationship right here, then I want AS 65005 paying me to send me traffic. So I don't want to pay somebody else, I want them paying me. So a lot of my policy around this is going to be done using AS path poisoning, various ways of not advertising the route, AS path prepend, other things that are going to try to shape my inbound traffic. I will say this, entrance selection in BGP is the hardest problem to solve. It is very, very difficult to solve entrance selection in BGP. Another policy I have is not traversing. So from AS 65003's perspective, I don't want traffic to traverse AS 65,000 to get to me. I want all my traffic to come in on AS 65002 unless it originates in 65,000 itself. So again, this is an entrance selection problem or do not traverse. Now, in theory, anyone can advertise anything they want in BGP. If you build a BGP peering session, you get a provider to build a peering session with you, and you get the stuff going, they will peer with you. Actually, instead of getting into RPKI, what we're going to do is it is 10 till. We will take a 10-minute break and give my voice and your brains a bit of a rest. Go grab some chocolate or something. I don't know. If you don't like chocolate, grab a root beer. I don't know, whatever it is. And I'll be back in 10 minutes. Okay, and we are back. Third hour. So I went and spent some time looking up the Quad 9 stuff to see what was going on there. Looking to see where I am on my slides as well before I start sharing those. Okay. Let me share this. Hopefully everybody's back. And raring to go. Had your chocolate or root beer, whatever it is. Okay. So this is a situation with Quad 9. For anybody who's interested. So we said before that what DNS does is it converts a domain name into an IP address. So what happened was that Quad 9, which is a recursive public, recursive nonprofit, recursive DNS service, was resolving names to a website that then pointed to other websites that contained copies of copyright material. Like so. So Sony sued Quad 9 in German court, stating that Quad 9 should not be resolving this domain name. Even though there's no copyrighted material on this particular website, it only has pointers or URL links to other websites that do contain copyrighted material. They say Quad 9 should not be resolving this domain name. Now, Quad 9's defense is basically we're a DNS provider. We don't chase all these links down to see what's behind them. We just resolve the name. So far, German courts have ruled against Quad 9 in this and said, nope, you should not be resolving these names. It's still an appeal and all sorts of other stuff. There's been another lawsuit filed in Germany against Cloudflare on very similar terms. I suppose from my perspective, the problem here is going to be that I'm not sure how Quad 9 can index the entire internet and know that there is copyright material behind one of the names that they resolve. I understand the point of what Sony's trying to do, but the problem will probably be before this is over with, is this is going to cause only companies that have search engines to be able to be DNS resolvers. If this is true, if this holds up all the way through to the Supreme Court of Germany and stuff, because only those companies will have the ability to index the entire internet and to trace out every domain name that they are resolving and make sure that they are not containing any sort of objectionable material. There's also some stuff thinking about here that you might want to think about in terms of censorship and stuff like that, centralized censorship and stuff like that. So that's the gist of the case. I'm not a legal expert, so don't take my word on any of this. You can go look it up for yourself and see what you think of it and whether you agree with Quad 9 or whether you agree with Sony on this particular point. But this seems like an area where there could be problems coming in the future. Quad 9, by the way, is the only, as far as I know, the only recursive server or recursive DNS provider in the world that is truly a nonprofit and is focused on privacy. So Quad 9 is a great place to set your DNS recursive server if you don't have some reason to set it someplace else, like OpenDNS or your local provider or whatever it is. All right, so back to RPKI. In theory, anyone can advertise any route they want to. So for instance, if IP address X is available at over here from AS65003, and in AS65001, somebody connects to AS65001 who's an attacker, and they just want to grab the traffic. they could advertise X to AS65001, causing AS65001 to advertise X to all of its peers, which could draw traffic um, from, say, AS65000 towards 65001 instead of 65003. So the attacker actually can grab the traffic, put it as a man in the middle, and push it to where they want to go across their servers. So this is a problem. This is about hijacking, if you want to know what the correct term is. So anyone, in theory, can connect the internet, advertise some route, and drop off. Spam operators, when I worked for a DNS provider, we saw this all the time in the DFC. We would see somebody attached to a provider, advertise some already owned address space, and then disconnect really fast, like 15 seconds, 20 seconds. And what they were doing is they were using that address space as a spoof address source for spam and for DDoS attacks and stuff like this. So one way that we can get around this or cause this to, or kind of help solve this problem, it won't solve all the problems, is something called the Resource Public Key Infrastructure, or RPKI system. So what happens in RPKI is that your regional registry that gives you your IP address will take your IP address and your AS number and bundle them together or sign them using a public key set. And then they'll keep the private key in private. This is shipped as a ROA, a route origin authentication. Now, what normally happens is a provider will not advertise this ROA directly. They will create a secondary ROA that's in there using their public-private key pair and advertise that ROA instead. This ROA is stored on servers and carried across the internet to a server that then uses something called the router RPKI protocol to communicate with routers running BGP speakers. So when a BGP speaker receives a route, which is the NLRI, the reachable destination, plus an AS path, one of the things included in that is the origin AS. That origin AS can be checked against this ROA to make sure that the origin AS and the IP address match. If they don't match, the BGP speaker can reject the route. They can throw it away, not pay attention to it, reduce their preference, other things like this, whatever they'd like to do. So again, the RPKI is not perfect. It doesn't solve every problem, but it solves some of the problems of route hijacking on the global internet. There are other things called BGP-SEC, which I'm not really fond of. And then there's a new one called ASPA, relatively new. And then there's SOBGP, and there's other solutions that solve more of the problem. Now, I will say that BGP you'll never get perfect security out of BGP. And you actually don't want perfect security out of BGP, because to get perfect security out of BGP, it would have such a huge operational impact on the way things run and handshake deals and stuff like that, that it would actually slow down the internet and peering and stuff like that in really radical ways. So there are some other systems out there. If you want to explore that a little bit, you might want to look at SOBGP and ASPA as examples of things that seem deployable and actually are usable. All right, so everyone here probably already knows about ping. But I have a little section here on ping. So ping is actually much more useful than you might think. It gives you reachability most of the time, or if the server will answer to it. But you can also do other things, like you can set the MTU of the packet or the size of the packet. So you can actually say try packets of different sizes. You can use different protocols. By default, Windows uses ICMP, and almost all Linux implementations use UDP. Or actually, I'm sorry, they all use ICMP for ping. I'm thinking traceroute. So I'm totally lost there. But you can actually do a record route using ping as well. This is in PowerShell in Windows. This is in Windows Subsystem for Linux. I'm showing over here. And it will actually do something similar to traceroute, but it doesn't work the same way. It uses the record route of the ICMP header. So ping is available on almost every command line. Here's some trace routes, same sort of a thing. What traceroute does is a little bit different. Traceroute, if you have a host and then a few routers and then your destination server, what traceroute does is it sends the first packet with a TTL of 1 so that you'll get an ICMP timeout on the first host or first router. With 2, so you get a timeout from here returned. With 3, so you increase your TTL with every packet you send, so you can actually get ICMP timeouts from every router along the path or device along the path. And as I said before, most Linux will use UDP, and most of your both of these are actually Linux, but anyway, most of your Windows machines will use ICMP packets to send those trace routes. But you can have all sorts of options with trace routes. You can do all sorts of different sizes of MTU and stuff like that. When you see a star in a trace route, that doesn't mean that it's unreachable necessarily. It just means that there was no ICMP response. So quite often, when you get, like 11, 12, 13, 14, and then you get an IP address down here, that means that these are just not configured to run ICMP timeouts, or they're blocked by the network or something like that. So another thing you can do with an IP address is you can look up the geographic location of that IP address in theory. Okay, not necessarily, because a lot of these geolocation providers don't work very well, just to be honest. They do their best to do what they can. KeyCDN, IPFI, Google's geolocation stuff, all of these things do their best to try to find the IP address or the geographic location of a particular IP address. So this one here, for instance, this is Nanog, and according to IPFI, it is in San Francisco. And IPLocation.net, it's in San Francisco. And then if you look at KeyCDN, it says looks like it's in Chicago. And then if you look at Google, it says it's at this longitude and latitude. Just give me a city. So these are the problem with some of these geolocation services is that a lot of these services are hosted behind what's called a CDN. And we'll talk about what a CDN is later when we get into provider types and the CDN business model and stuff. But these are hosted behind CDNs. So, and a lot of these are actually unicast addresses because they're hosted behind CDNs. So when you get a single address and you say it's in San Francisco, well, the server is probably not in San Francisco. The server probably is in Chicago in this particular case. The host is probably in Chicago. But if you're somewhere on the West Coast, you're going to go through Cloudflare's CDN to get to this server. So it's going to look to IPFI as if it's in San Francisco, which is where the Cloudflare entrance point is. So you can do this, but be a little aware of whether or not these results are accurate because of these things being hosted behind other things. Or having unicast addresses. So if you look at 193.0.6.139, this is RIPE's IP address, which is another user group out in Europe, or network operators group out in Europe. And you'll notice that this one shows it in Amsterdam, this one shows it in Amsterdam, and this one shows it in Amsterdam. RIPE does not host their server in somebody else's data center, or do they run any sort of CDN or any sort of caching service in front of them. So it's more accurate in the case of write. So what about who owns an IP address? Here we go back to Aaron and RDAP and who is. And here you can find, again, that the full name and handle, address, and etc. are often available in who is or RDEP. So this is just another part of that who is record I showed you earlier. So that is all of that about routing. So now let us talk about another interesting area, which is providers and peering. So I've talked about routing, but routing is done by providers. The actual traffic carried through the internet is carried by providers over long haul links and stuff like that. So let's talk about some of this stuff. Let's talk about a packet path. So let's say that I'm here at this host and I'm connected to my corporate network. I call that an enterprise. I don't like that term enterprise, by the way. But unfortunately for me, I have not come up with another name to use for these types of companies that only do not use the network as they don't use this network as a service. They don't sell the network as a service. So the path of a packet is going to be from this host through this enterprise network, through an access provider. And then once you hit the access provider, you're in the DFC, the default free zone. Then you're going to go either up through internet exchange points, through transit providers to a content provider, or you might go through some other path, or as we'll talk about in a little bit, the content provider may actually have a link directly to the access provider, and your traffic could go directly into the content provider's network. So we're going to call this my last mile network and an access provider. This is both going to be both of these things. We have these kinds of providers to talk about. We're going to talk about internet exchanges, transit providers, content providers, and access providers. So those are the 4 different classes of providers we want to talk about. Before we get there, we want to talk about peering. So there are various kinds of peering between these various types of providers. So I said we have 4 providers, 4 kinds of providers we want to talk about. So these providers peer in specific ways. There are what are called internet exchange points, or IXs or IXPs, and we will talk about those in more detail later. There's what's called private peering. So this is very similar to an IX in that 2 providers like, say, AT&T and Verizon will get together and say, I have a lot of traffic that goes through this peering point or goes through Chicago to get to you. How about if we just rent a facility, a private facility, we'll both drop circuits in and we will peer with each other privately. Then we also have a provider serviced or a purchased access or upstream. Now we're going to talk about other kinds of things in this realm here in just a minute. But you basically have peering at private peering points, internet exchanges, or what are called COs or points of presence, POPs or points of presence, or COs, central offices. At these places, there are 4 kinds of peering that you can have. What are called provisioned, which is like an enterprise or a downstream pays for upstream, pays for access to the internet. In this case, I would not have transit, what's called transit. This network, this enterprise network, is not designed for carrying traffic between 2 providers. So these are not transit or non-transit networks, and they should never transit traffic between them and somebody else. So typically what you'll see in these situations is this router will actually filter on the AS path. They'll say, your AS is AS 65,000. I'm going to filter you so that you can only advertise routes originating in AS 65,000. So if there is some other AS back here of some type, those routes will never be accepted by the upstream provider, and they just go away. Those routes go away, and you can't transit stuff. Now, paid transit is when one provider pays another provider to carry their transit to their traffic to the internet. So here When I put the check mark here, I mean this is a transit peering session. This provider, this upstream provider, will accept AS paths with some other AS in the AS path. So this provider here can actually sell upstream to some other company or some other organization if they want to. Now, settlement free is usually means that a provider peers with another provider when no money changes hands. So when one provider pays another provider or a customer pays a provider, that is called settlement. In the parlance of the DFZ, of the provider world, it's called settlement. So settlement free just means I'm going to peer with you and we're going to be able to exchange traffic. But because we have equal amounts of traffic going to one another, we'll call it settlement free. Now, quite often, settlement free is non-transit. Very rarely you will find a transit settlement free peering session. Most of the time, this is going to be non-transit. You're not going to have people with ASs behind them transiting through a settlement free peering session. And then we have what's called open. So open peering just means that I know as a provider, I am not going to get money from you for carrying your traffic, but I'm going to carry it anyway for some reason. Now, why might I do this? I might do this because, for instance, you're a college, you're a local community college, or you are a research facility of some type. So I'm going to be nice to you, or a high school, and I'm going to give you internet service for free, basically, by giving you open peering. Now, we'll talk another situation later when we talk about centralization of the internet, where open peering is where somebody like LinkedIn or Microsoft or Google will go to an access provider like Comcast or ATMC or whatever, and they will say, we want to put a router and drop a link into your point of presence or your central office in a given region. And I'm going to drop this link in there, and I'm just going to give you this information. So you're just going to give me the traffic directly rather than going through a transit provider and paying your upstream. So open peering will often happen between content providers and transit and access providers as well. But again, we'll talk about that more later. So one of the kinds of providers we want to talk about is an access provider. We talked about 4 different kinds of providers we want to talk about. The first is an access provider. This is a kind of combination of different access provider designs that you might run into or you might see. So access providers use different edge technologies like DSLAM, which would often be older style Wi-Fi, LTE, DSL, satellite, etc. would use DSLAMs. It's a kind of modem system that you would use. DSLAMs are becoming less common in the modern world. Typically what we have now is we have a cable access through something called GPON, Gigabyte Passive Optical, or I'm actually sorry, I did that wrong. This is not cable access, is going to be through DOCSIS. I have my eye in one place on the slide and I'm talking about another place on the slide. It's going to be DOCSIS. A lot of this is going to be DOCSIS, which is going to be your RG58 cables that you have coming into your house, fiber to the curb, and then RG58 down, where they steal channels off of a cable television system to give you upstream and downstream data. This is all going to be DOCSIS. DOCSIS is currently in 4.0, but not everybody has that deployed. But that is where that's the most current standard. Over here, you're going to have a metro fiber ring. This is often going to be DWDM, or if it goes out to individual houses and individual businesses, it's often called GPON, which is a passive optical network. Because it's called passive because the device out at the remote site, at the customer site, does not have any power on it. Now, these metro fiber rings, if they're running DWDM, will have what are called ROADMs or ADMs, add drop multiplexers. This is a random optical add drop multiplexer here, and it will pull off different wavelengths of light and hand them off to a router to connect to a building or a user or whatever it is. Now, all of these different types of last mile access are going to come out to the core, the POP, the core, the central office, whatever it is, of the access provider. And then the access provider is going to connect to one or more transit providers to give you access to the internet. Now, they also can connect to an IX or an IXP that allows them to connect to other local providers or to the internet through transit providers. Now, another very common kind of access network you're going to run into nowadays is a 4G access network or a 5G, a cellular network. Now, I'm not going to go into a ton of detail here, but essentially what you have is you have towers with antennas on them that are running 2 to 6 gigahertz radios. And down at the base of this tower, you'll have a base station. That base station will actually convert those signals from wireless signals into optical signals to be carried through the radio area network, through the RAN. That's then gathered up through a backhaul network to a mobile core. Now, your wireless devices, like your cell phones and tablets and stuff, connect to these radio towers using 4G or 5G radio signals and systems. And then this mobile core is going to be different depending on whether it's 4G or 5G. So a 4G mobile core uses proprietary hardware and software at these different in the mobile core itself to do things like, what do you do in the mobile core is you're going to do things like billing, make sure the person's authorized to access certain services. All of that stuff is done down in the mobile core via various software packages. In 5G, this mobile core becomes a data center and everything is open source and disaggregated so that you have packages that you install on standardized white box or gray box equipment that you're installing out there to run this mobile core. Now, the mobile core at the edge is going to connect to the provider core, which allows you to access any services and customers of the provider. And it's also going to connect to the internet so you can connect to the global internet. Now, you might think that this traffic coming across this RAN would be some type of voice traffic, like in the old POTS, plain old telephone days. It's not. Here at the tower, everything is converted to voice over IP. Everything is carried over IP in all of these 4G and 5G networks. You don't have real voice networks any longer. There are a few POTS networks out in the real world where you actually have a telco switch, like what I used to work on. If you want to hear about that, you have to come to my data center fabric session because I talk about some telephone network stuff there. But very few of those networks exist any longer. Most of this stuff is now all digital and it's all voice over IP, almost all of it. So we used to carry IP over voice lines. Now we carry voice over everything IP. In fact, the voice over IP doesn't even happen here. It happens all the way back at your mobile device nowadays. Okay, so let's talk about access providers' service models. What is their economic model? How do they make money and where do they spend money? Because this will help you understand, first of all, if you're in the access provider business or thinking about going to work for an access provider, this will help you understand kind of what they do, how they make money, where their revenue is, and where they spend money. And if you're calling an access provider for service, this will help you understand a little bit of how this works. So their income is primarily going to be user access fees, business services, and physical plant rental, like co-locating. So if Google comes to Spectrum and says, we want to rent space so we can put Google servers in Spectrum's physical facilities to get closer to our users, then that's something that Google is going to pay Spectrum to do. Verizon, AT&T, Viasat, all of these are edge providers or access providers that give you that get paid for these types of things. Their expenses, their number one expense is going to be people. And that's going to be true for every business we talk about. People are the most expensive thing in running a business of this kind. Your second most expensive thing is going to be your infrastructure, your buildings, your network software, your hardware, your servers, all those kinds of things cost money, and you're going to pay a lot of money for them. Now, another thing that people don't think about is right of way. We're talking about right of way more again when we get to transit providers. But right of way is very, very difficult. For instance, if you decide you're going to start an access provider, and that means that you want to go out to a neighborhood that's not got service right now, and it's all above ground poles. So there's all these utility poles running the street, and you want to attach your cable to these poles. Well, poles are rated for a certain amount of weight. There's a weight rating or a weight limit on every one of those poles. Cables weigh a certain amount. So if you, particularly when you do maintenance loops where you wrap up a bunch of cables so that you have cable you can pull in case there's a breakage someplace so you can repair it. So this weight, if it's added to all these poles and it drives the pole weight over what the pole is rated for, you as the access provider may be required by law to rip up every one of these poles and replace them throughout an entire region. This can be very expensive. There's a lot of legal stuff that goes on here. Some states and some cities will force the electric company or other people, utilities already on the pole to pay for part of the cost. Others put the newcomer, force the newcomer to pay for everything. So like if there's going to be a power outage because you have to take a pole out, the newcomer has to pay a fee for that, et cetera, et cetera. It's very expensive to do this. Now, another form of right of way is just getting next to a street. If you have a street with a bunch of houses on it, and you're going to bury an optical cable down the street to support all these houses, the company is going to, or the city is going to want a fee for burying that cable in their right of way. And you also have to make sure that you don't damage any water, sewer, any electrical power that's buried alongside it, et cetera, et cetera. And if you cross driveways, you have to pay for cutting the driveway and fixing it, or going underneath the driveway with micro boring or something like that. And if you have to cross the street, you have to pay for the fixes in the street and stuff like this. So right of way is very expensive. Finally, these access providers don't cover a lot of geographic area a lot of times. So they have to pay transit providers to get access to the internet, just like you or I would. So this is another expense that they deal with. Right, just checking for questions real fast. So these are the business, this is the business side of an access provider. Now let's talk about internet exchanges. It's the second of the 4 kinds of providers I wanted to talk about. So back in the bad old days, Brazil and Costa Rica, for instance, I'm not sure this is actually true because I haven't spent a lot of time trying to remember when we put in IXs in South America, but perhaps Brazil and Costa Rica are on different sides of mountain ranges or distant enough that they cannot be physically connected for some reason. So what you do in this case is you would normally connect Costa Rica to a provider in Miami and Brazil to another provider in Miami, and all your traffic from Costa Rica to Brazil would go through these providers in a connection point in Miami. Well, obviously this is not very good. If you have a video provider who's trying to provide videos of the rainforest or the chocolate farms or whatever, plantations in Costa Rica, over to Brazil, it's going to go all the way through Miami. And that's really going to stink. Your delay is going to be horrible. Your service is going to be horrible. So what you tend to do is you tend to build, and by the way, we had the same problem in Southampton and Edinburgh for a long time. So it's not just like South America. It's like all over the world, China, Middle East, Far East, all these places. Everybody was going to central locations to get to things. This is how your GPS routes you when you put 2 locations in a car, right? It takes you to the nearest high-speed highway, takes you to the closest exit to the destination, and takes you off as late as possible on the high-speed highway. Not always the best route, but that's what they do. So local IXs were originally designed to allow inter-country or intercity communication within a region, to unify the region so that providers in the region didn't have to pay upstream and carry their traffic across long distances. This was the primary purpose for Internet exchange points. Now, over time, Internet exchange points have gotten a lot, they do a lot more. So, for instance, nowadays, most Internet exchange points have Amazon, Microsoft, Google Cloud, Akamai, Cloudflare, Fastly. All of these companies go out and put physical hardware in the Internet exchange points racks and connect them directly to the exchange point fabric. So if you are a member or a peer in the exchange point, you can connect to all of these cloud services directly. Or if your local provider is a member or a peer, you can connect to your local provider's router, pay them an upstream, and connect directly to all of these services. Amazon Web Services calls this, I think, a regional direct connect, a regional DC or something like that. Akamai uses a lot of this as well. So all of these companies do go into these IXs. Now, IXs also can provide other kinds of services like, I don't know, DDoS protection locally. Sometimes you'll see people that will do email spam filtering within the IX, between servers, between mail servers. So they might offer lots of other services besides just connectivity at this point. But essentially what the IX is going to provide you with, the Internet Exchange Provider is going to provide you with, is a fabric that connects everything together, which is either going to be a layer 2 or a layer 3 fabric of some kind, and then a route server. So what happens here is each member or peer peers with the route server rather than peering with one another. And then if you want to exchange routes, say between A and B, rather than building a BGP peering session, you would simply go to the route server and say, turn on or turn off filtering between our BGP speakers, so that now that routes are carried up to the route server and down to the other router, the other BGP speaker. So this helps scale these peering points in a very rational and very good way. So let's see, Internet exchanges like Lynx and Equinix and Grix and Stockholm Internet Exchange, and this is not all of them, but this is a few of them I found on the internet, or companies that I've worked with and around a bit. They have the usual costs, things like people. Number one cost for every provider in the entire planet is going to be people. And then they're going to have infrastructure. They have to have a building to put all of this equipment into. And if they provide upstream or they need upstream, they're going to pay for their upstream transit. Now, the way they make their money is through user access fees, like you pay to, physical plant rental, you pay to put a server in the rack. You pay for the power that server. User access fees like memberships. You may pay a certain amount just to join the IX so that you're a member, which gives you access to the physical plant in some way. Fabric connections. Some IXPs will charge you per fabric connection and per speed of fabric connection. They'll charge you for routes that are reflected or carried through the route server, those types of things. So these are all types of services and stuff that IXs will get money from. All right, so the third type that we want to talk about is transit providers. Cogent is an example, just one example of many, of a global transit provider. Again, there are many others. There is AT&T, Verizon, blah, blah, blah. I just picked Cogent because they had their map available, quasi-map available on the internet, and it was easy to find. So Cogent is an example of a global transit provider, a very large global transit provider. And you can see that they have on-net and off-net pops, what they call on-net and off-net pops, or points of presence in lots of cities all over the world, all the way down to, Mexico City, Guadalajara, all throughout Europe. And we'll talk more about this cable here and these cables. We'll talk a little bit about undersea cables in just a minute and how these are done and what they do and stuff. And interestingly, you'll notice that there's actually connectivity up into Greenland and through Ireland and stuff. You'll see that there's connectivity up in these upper reach Nordic areas as well. So this is an example of a global transit provider. There are more regional transit providers like XO, which tends to operate only within the United States. Regional providers will tend to have a denser connectivity within the region they serve. So you can see XO has a lot more connectivity than Cogent does just within the United States. That's because that's their area of focus, and they're trying to provide more services to smaller cities. So oftentimes, if you're in an off market or a secondary market, you're better off looking at a regional provider that's then going to charge you a bit more because they're going to pay transit for their upstreams and stuff. But this is, I don't know how recent of a map of XO this is, but this is XO's network. Now let's talk about undersea cables. Now, this is from 2019. This is 4 years old. I haven't checked recently, from Telegeography and submarine. So you can go to this website and they will put you a map up of all the submarine cables. And you'll notice that there are a lot of submarine cables. There are a lot of cables running through the ocean and through like the Mediterranean and through, I don't remember what this is, some bay or whatever. And this sea over here, and then the Chinese, the Sea of China and stuff like that. You'll see all of these areas. And you'll notice an interesting thing here. There's a lot more cables running through the ocean between coastal points than you might expect. You might expect these cables to go over land. And normally they don't because there's rough geography, mountains and stuff. And because you got to pay a lot of right of way, particularly when you go between countries, it's very difficult to get like from Brazil again to like Costa Rica or something. So quite often what you'll do is you'll go through the ocean to get there. Greenland is a perfect example. There are basically no on land Greenland optical cables. Everything in Greenland runs through the ocean. And that's because Greenland is very extremely hard territory to run cables over of any kind. You can't bury it. You can't do this stuff. Let's see, there's a comment. Is this IX stuff public information? Yeah, there is. You would not use whois to find out who connects to which IXs. You would use something called peering DB. Yes, that's correct. You actually listed in your comment here about peering DB. Some information is lacking out of peering DB, particularly for private peering points that won't be there. You can also sometimes go to, like, if you know that you're looking at Equinix or Lynx, you can go to their website and they'll sometimes have a list of who their customers are. Again, those may not be complete, but that is, you're going to have to sniff around. Some of these things, or people don't want to tell you who they peer with and where they peer. So it sometimes takes a little bit of time. The cable service life for these cables is 15 to 25 years, by the way. I think it's longer now. They're building different kinds of cables. So I don't know. That's something to think about. How do they lay these undersea cables? You like my ship? Isn't that really cool? Anyway, what they do is they have a specially designed ship or barge, particularly in seas like the Mediterranean and in bays. They'll use barges to lay undersea cables instead of full-on ships. They'll just pull the barge with a tugboat. But anyway, this is kind of what they do. They have a cable reel or a bunch of cable reels, and that cable reel drops the cable to a sled, and the sled is dropped using a crane off the side of the boat, and then the sled is attached with a tow line, And the cable, the tow line pulls the sled along, and there's like a little burying jig underneath there, like a blade or something, or a plow. Normally it's called a plow, and that cable is buried under the ocean floor. Now this isn't always true. You will get to places where there are valleys and things like that that you just can't get deep enough with the cable, and they'll just float it across that. They'll have weights that hold the cable at a certain depth, and they float across that space. So there are various ways this is done. Normally, a submarine cable is made up of fibers like a gel coat. This gel coat prevents water from getting in. It's your final defense against water. You'll have a copper or an aluminum tube. This is partially to provide strength, but it's also to provide you a ground, because your ground differential between the different places is going to be very bad. You may also need to carry power across this cable to support repeaters and stuff, because you don't really have power outlets on the bottom of the ocean that you can stick a plug into to support a repeater. This is going to be polycarbonate, which is going to support this or separate this ground from floor, which is your aluminum water barrier. And then these are steel cables that are designed to give the cable strength. And then you're going to have a mylar tape water barrier, and then you're going to have a polyethylene water barrier. Now, again, some cables are much smaller than this now. Jeff Houston just posted on his blog a couple of months ago, within the last couple of months, I think, on the lighter weight cables that they're using now in bays and other areas like this. All right, now let's talk about satellite. We have 3 minutes. Maybe we can talk about a little bit about satellite before we jump into a break. So satellite comes in two forms most of the time. There's LEO. I'm sorry, I did that backwards. This is geosync, and this is LEO. Now, there is middle Earth orbit, but I don't know of a lot of systems that use MEO satellite systems for communications. Geosync, the beauty of a geosynchronous satellite system is that no matter how the Earth moves, the geosynchronous satellite is directly over the same point on the Earth constantly. So if you have antennas on the ground that are pointing up, they always point to the same place. They don't have to be adjusted constantly. So that is the beauty of a geosync. The other beauty of a geosync is it only takes 7 to 8, maybe 10 geosync satellites to cover the entire Earth, because they have such a broad coverage space, because they're very high. They're in a very high Earth orbit, it's called. So these high, middle, and high Earth orbits cover a lot more space just because of the cone that they do. Now, the biggest problem with a geosync satellite is this distance is so long, you get very high delay. This is why a lot of satellite systems have high delay, is because there's geosync. Now, LEO, like Project Jupiter, I'm trying to think of some of the other ones, Starlink, there's 4 or 5 of these out there, maybe even more at this point. I don't remember all the names. I do try to keep up with it. How thick is an undersea cable? The thick ones are 10 inches, 8 to 10 inches, I want to say, maybe a little bit less than that, could be as little as 6. The newer ones, some of the newer ones without all the heavy steel stuff in them for shorter runs are maybe an inch or less. So it depends on how far the run is. So an LEO satellite is much closer to the Earth. So you have much faster or much shorter delay, because you're just traveling across less distance. The problem with an LEO satellite is, a low Earth orbit, is that it doesn't stay in the same place relative to the Earth's surface. So you have to have a movable antenna. Used to. Now we use something called beamforming to make the antenna virtually move or move its signal pattern without physically moving the antenna. So beamforming is almost a necessity for these LEO systems like Starlink and Jupiter and some of the other ones. These satellite systems, because they have such a small scope or a small cone of service, require hundreds to cover the Earth's surface. So I don't know, I think Starlink was supposed to be 1,200 satellites or something like that. Now, there are problems with this in terms of just space usage. How many of these systems can you put up before you literally start blocking starlight and stuff like that, and sunlight and stuff like that. Like, how many of these can you put up before you start running into problems? So this is the difference between LEO and geosync satellite systems, just to give you a sense. All right, we're going to take, again, jump out to a break, and then stop sharing my screen. We will come back in 10 minutes, so like one after, and we will hit the next 25 slides or so. Should be the last section of this mess. And I know your brains are getting really full, so go take a 10-minute break, and we'll come back and talk about transit providers just a little bit more. So here we are back again, talking about LEO and geosynchronous satellite systems. Um, I think we're pretty much done with those, however. I think if there was something else that I meant to talk about there, but I can't think of anything off the top of my head. There's more to say, I'm certain, but there you go. All right. All of these types of systems are used by transit providers. So let's talk a little bit about the income and expenses for transit providers, just so we have a sense of um, what their what their financial picture might look like. So obviously, their income is going to include user access fees, services. Services are the biggest and growing piece of transit providers. As an instance, Verizon used to have 3 or 4 networks: Verizon Public IP, what was called PIP, Verizon Business, and then the Verizon Wireless Network for their cell phones. The Verizon PIP and Business Network were not making a lot of money. The Verizon Wireless Network was, so they merged them all together under Verizon Wireless. So a lot of times your services like cell phone usage and stuff like that are your big money makers. Hosting, other things like that. Those are where you make most of your money. Your user access fees are not generally where you make a ton of money in these large scale companies like this that are global providers or regional providers. They do rent out their physical plant through dark, dim, and lit fiber, various ways of renting out their fiber to other people. Companies like LinkedIn and Microsoft and stuff will rent dim fiber or dark fiber or even lit fiber from a company like this, particularly for undersea and long run cables that they happen to own, and rights of way that they have. For instance, if you want to do a regional provider or a local provider, you can go to AT&T or Level 1 or Level 3 or somebody like that and say, all right, tell me about all the rights of way you already have in this region, so I don't need to go get all of it. I can buy some from you. By the way, a lot of these providers will also buy their rights of way from railroad companies, because railroad companies in the US and in many other countries had legal right of way precedents way back in the 40s and 50s, and they have tons of right of way in all sorts of cities, even in the downtowns and stuff. And public transit systems as well are a common place to get rights of way in large cities, bridges and port authorities and stuff like that. So where they spend their money is people is always number one. Of course, they have a lot of infrastructure, particularly as you are running very global, large scale networks. You have a lot of infrastructure. Right of way is going to be a major cost for these people. And then sometimes they will pay transit to other transit providers for various reasons. Now let's talk about edge providers, primarily something called content distribution, but they also do DDoS protection and acceleration. And they provide DNS services and lots of other things as well. So edge providers are companies like, well, I'll have a list of them later, so I won't talk about it right this second. So edge providers, like I said, if you have content sitting out here as Google or Microsoft or I don't know, whatever, you want that content to be closer to your users. How do you do that? Well, edge providers will have co-located in almost every access provider. Give you a sense of scale. I think Akamai at last count had 140,000 servers or 500,000 servers or something. It's a huge amount. In all of these access providers and in these internet exchange points, they will actually have all these. So you can transfer data to the content provider or the content distribution network, the CDN server, and it will be served locally to your users. Now, another thing that these companies will do is they will actually have their internal network that's in parallel to the internet. They will have a network, a termination point here, an acceleration point here. So your TCP session comes up to this acceleration point, is terminated, traffic rides the internal network of the content provider, comes off the other side, goes through the internet to the content provider. So instead of going across the global internet, it goes across the provider's network. And this can accelerate traffic a lot by doing various things with TCP timers and stuff. So there's a lot that these edge providers do. Another thing edge providers provide is security as a service. So say that you have a web server sitting over here, and somebody tries to DDoS it. They send terabits of traffic, 2 or 3 terabits of traffic, towards your server to try to shut your server down. Well, how do you solve that problem? What happens here is the edge provider consumes all of your traffic into a scrub center or into a point of presence or whatever you want to call it, and then ships the traffic, clean traffic only, back down to the internet to your content, and then relies on you to be able to reach back to your server or to your users. So this allows you to deflect and destroy large-scale DDoS attacks and even drip attacks and other kinds of things. So a lot of these companies will focus on being able to block all sorts of different kinds of attacks. They'll have web application firewalls that block faulty access to WordPress sites and Joomla sites and things like that. They'll have just all sorts of services that they can offer in this space. These edge providers place their servers, like I said before, in internet exchange points and in access provider networks, so that you're much closer to the user. You want to be able to load all of your fixed content as close to the user as you can to reduce the round trip time so that your users get a better experience. When I worked for LinkedIn, we got a daily email that told us how fast the website was or how fast the service was from lots of different locations, because a lot of users will disconnect or ignore you after like 2 seconds or 3 seconds. Even if it takes more than 1 second to load your site, they will switch to another site, get bored, switch to another site, and start doing other things. So if you really want engagement as your primary way to make money by selling ads and stuff, you have to be very, very fast. So dedicated CDN services like Akamai and Cloudflare, the two that I give here, Fastly is another one, make their income off of content distribution, cloud service connections, DDoS protection, ad placement, geolocation, and etc. They can also get income off of colocation and dim and dark fiber for their own networks, because a lot of these companies run global networks that are extensive and have a lot of bandwidth. So they can actually sell a little bit of their own network sometimes in different locations. Their expenses, always number one, is people, infrastructure, colocation fees, and sometimes they pay transit. So these are all the different ways they make and spend money, these edge providers. Oh, if you didn't know this, I work for Akamai right now, so that's why I'm investigating, spending a lot of time learning about what these providers do and how they work. And I have a lot of friends who work at Cloudflare and at Fastly, so this is an area that I've kind of been spending some time looking at and trying to understand better. All right, so let's talk about cloud providers. What do we mean by a cloud provider? A cloud provider like Google or AWS or Amazon or something like that, it's just going to provide bare metal servers, virtual servers, storage and services, and things like this. This is all cloud computing. So anything within the cloud computing space is here. The last number I saw was that about 60% of the processing that goes, information technology processing that goes on right now is going on in cloud providers, in the cloud space. So this is a very large and growing service area for people. And you'll find all sorts of different kinds of services here. We often do these, we call these like infrastructure as a service, software as a service, all sorts of different things that you'll find in this space. And now we have network as a service and all sorts of other things that you'll find here. So these are cloud providers. Now, cloud providers tend to make their money by simply renting this information out or these services out, and then they spend money on people and infrastructure for the most part. They will spend money on transit as well, depending on what's going on. Content providers are companies like Google and Amazon that you will find. They make their money by increasing engagement and purchases for the most part. Now, it is true that companies like YouTube will take your uploaded content and essentially sell it to other people by injecting advertising. So that's how they make their money as well. We're going to talk a little bit more about the entire ad marketplace in just a second and surveillance capitalism. But this is the basic process for a content provider is they're going to use surveillance and analytics to build a profile that then is used to build a filter that directs censors, content, and sellers through this filter to increase your engagement with funny cat videos and give you videos and take your uploaded content and feed it back into the filter for other users and then purchases. These people are primarily focused on what you might call, I still spelled it wrong, didn't I? The nudge. If you want to understand this marketplace really well, there is a book by Shoshana Zuboff called Surveillance Capitalism, The Age of Surveillance Capitalism that's really good. There's a couple of others. There's one called The Nudge. Now, Shoshana Zuboff's book is very negative. The Nudge is more positive or more neutral on these things, but you'll find a lot of information there that you can look at. Okay, so we have what's called the ad marketplace. This is how a lot of these companies make their money, is via the ad marketplace, which is this. When you go to load a website, now not rule11.tech, because I don't keep ads on rule11.tech, but a lot of websites do have ad placement slots. In your web page, you can put an ad placement spot or a slot, and you tell it how large that slot should be on the page, how much room it should take up. When that page is loaded via the CDN or via the web server, depending on the ad placement network, what happens is the web server is directed, or the CDN is directed to contact an ad service. The size of this slot and the stats of this website are loaded to the ad service. The ad service then grabs this user profile that's been created by content providers and other people by doing surveillance and analytics on you as a person or each person, and they try to find a user that matches or a class of users that would be interested in this ad. They re-inject that ad to the ad service, injects that ad to the web server, where it is then posted into the website itself. This happens in mere milliseconds while the page is loading. This is usually done, this ad service usually puts out an auction for this slot, which people who want to advertise to this user profile on this particular site will then bid on that. And then what happens is that if you click on it, this gets the advertiser money, or it gets the ad service money. And then in theory, they're looking for what's called a conversion, which means you buy something and make them money. So this is a very large market. It's a very wealthy market. There's a lot of stuff that goes on in this ad marketplace. This has been going on for a long time. And this is why people do cookies and browser fingerprinting and everything else, is because they're trying to build this user profile so that they can sell these ads. So content providers, what do they do? They make their money off of services like geolocation, content distribution, cloud service, just selling stuff. Amazon makes a lot of money off of marketplace fees for other people to sell stuff through Amazon. There's a lot of money in that. So that is another thing. Data, which again, it's I would call behavioral excess, what Shoshana Zuboff calls behavioral excess. So their number one expense is always people. They also have a lot of expensive infrastructure in terms of hardware, networking hardware and software and servers. These people build really huge networks. Okay. Now, scale wise, we are talking millions of servers, not even hundreds of thousands, millions of servers scattered throughout the world. They are paying for all of that physical hardware and stuff out there, co-location fees and transit. Now, not all of your cloud providers are going to pay for transit. And that's because they're going to do something. They're going to go out and co-locate at the edge of the network as much as they can. Some examples here are AWS, Microsoft, Alibaba, DigitalOcean, Amazon, etc., etc. All right. Now, let's talk about some more governance structural things here for a minute. And I don't ever, when I'm talking about these things, want you to think that I'm pushing a particular point of view or a particular way of seeing things politically or whatever. This is more along the lines of, hey, you're in this session. Let me tell you a little bit about what's going on. You can think about it yourself and decide where you stand on these things. Just like with the Sony Quad 9 thing. I mean, I have my own opinion, but some people are going to think Sony's right. Some people are going to think Quad 9's right. It just depends on your perspective, and you need to make up your own mind and think about those things. So this section I call reshaping of the internet. I've spent a lot of time thinking about how the internet is being reshaped. This is the way things used to be. Content providers would buy upstream from transits, who would then transit to other people, go down to IXs and go down to access. So the core of the internet was in these transit providers. There were a few IXs that might possibly be considered as part of the core, but most of the core of the internet would have been considered these transit providers and nothing else. Over time, what has happened is this is totally changed. How would I want, if I were a content provider, to get closer to my users who are down here connected to my access network? What I do is I build direct links out to the IXs and out to the access providers, and I load up my content in the local access provider paying a co-location fee. So what I'm essentially doing is cutting the transit providers out, which of course costs them money and forces them to do more in content to survive. So this is the way that these things work. Now, CDNs like Akamai, Fastly, etc., kind of contribute to this flow of things as well by pushing content to the edge. Now, it's very good that content makes it to the edge because content at the edge is faster and more people use the internet and use it and engage with internet services a lot more the more the content gets to the edge. So again, what most of these companies are going to do, these big content providers, is they're going to peer directly with IXs and access providers, and they're going to stick their data down here. This also allows you to build a custom peering device. I've actually participated in designing a couple of these custom peering devices that are set up just to carry the right kind of content for a given service. So this gives you a lot of capabilities by doing this. Now, another thing that you'll notice that's going on is in order to do this kind of pulling stuff across and doing things and getting more content closer to the edge, is a lot of these content providers are actually building their own long-haul undersea cables and renting parts of that bandwidth back to transit providers and other content providers. So for instance, Amazon, now this is 21 and 20, this is a little bit older and I don't know exactly what they're running today, ran the B2BE in 21 and Jupiter in 20, covering the west coast of the United States, Japan, the Philippines, and other places over here in China and Hong Kong. They also ran an Australia and Pacific cable down called Hawaii that carries down to New Zealand and Australia. Google has a bigger footprint in undersea cable than Amazon does, and Facebook even has a bigger undersea footprint. But all of these large companies are building or laying their own fiber optic cables to carry their traffic between their data centers and to get closer to their users. Now, there are some other centralization drivers that are going on. For instance, I talked before when we talked about routing that BGP is the routing protocol that's used for running the internet today. When I first started at Cisco and got access to Cisco iOS source code, BGP was about 40,000 lines of code. Okay, this is 1996. Between 1996 and now, I know that Juniper's implementation, for instance, is over 250,000 lines of code. I don't have access to Cisco's any longer, so I don't know how big it is. But I remember when iOS was broke 1 million lines of code, and at least a quarter of that was BGP. If you go look at FR routing, which is open source, and you look at the files, and you look at BGPD, which is the BGP implementation, there are over 130 files just in BGPD. I don't know how many lines of code are in each one of those files, and this does not include the CI/CD system. So I don't know how big this implementation really is. I've never bothered to count. But DNS is much the same way. There are entire presentations on the complexity of DNS and how DNS is so complex and so hard to implement now. Particularly, there's something now called the D record, which is a new kind of wildcard, and it is made DNS not atomic any longer. It's very difficult. So another thing that you get into is Kai-Fu Lee's cycle. They call this the virtuous cycle. Kai-Fu Lee does. There's a book called AI Superpowers about this. The more you know about a user, the more you can attract the user. So the more you know about a given user, the longer they will engage with your service because you can build your filter to engage them more, to hand them content they're more interested in seeing. So you actually increase your engagement the more you know about a user. So you are driven as a content company to find out more about your users in every way that you can. And the more you know about users, the more you attract new users. And then there's the network effect, which is the other side of this kind of, or the same side of this same kind of thing, the other side of the coin. Having more users makes it easier to gain new users. So these are kind of drivers towards centralization. So here are some sobering statistics on centralization and how centralization is building on how we're centralizing a lot of things. Mobile phones. Android phones are 71% of the market. iPhones are 29% of the market. If you add things, 71 to 29 in your head, you come up with 100. There are essentially no other mobile operating systems being widely used right now, not even to the 1% point. All the others don't even make up 1%. Browsers. 62% of the browsers are Chrome. 21% are Safari. There's some amount that's Firefox in here, which I don't have. The remaining market, like Edge, Brave, Opera, they're all Chromium based. So they use the same source code as Chrome. I would say the Chromium base is about 75 to 80%, perhaps even more now, because I haven't looked at the numbers in a bit to know where Safari is. There are 8 content providers that account for more than 70% of the volume of the traffic on the internet. So Akamai, I don't really consider to be a content provider. It's a CDN. Take Akamai out, though, and you go Google, Microsoft, Disney, Netflix, Meta, Amazon, and Apple. 70% of the volume of the network, of the internet. So that is a lot. And that's from 2023. So some negative effects of this centralization that I point out, again, you don't have to agree with me about these. These are just things that occur to me as I am looking at stuff and trying to figure out like where this goes, is it's harder to escape surveillance. There's only a couple of email systems now that are not deeply surveilled. New entrants struggle to create space for their product. How would you compete with Amazon if you were going to sell stuff? It's actually kind of hard. There are people who do it in very niche markets, but it's kind of hard. Open source suffers. This is something I personally deal with a lot because I'm a maintainer for an open source routing project, FR Routing. And we kind of rely on a few large players, and there's very little financial motive for large organizations to support these projects. And standards, the IETF and ITU and stuff, tend to be driven by a few small number of companies. It used to be that Cisco dominated the IETF. Then Juniper came up and did a lot to break that hold and make it where it was more of a multi-vendor party, the IETF. Now it's Microsoft, Google, et cetera, that dominate the IETF. And it's just a few large players that do this. Now, another thing is fragmentation that we're running into. So a lot of countries are doing this thing where they want you to keep the data within the country where the citizen lives. This helps drive fragmentation. Another thing that helps drive fragmentation is that these large companies live in different companies. Like, you might think of Google as being universal. The reality is Alibaba and TikTok are larger in China probably than Google. So there are companies like WeChat and whatever. So you kind of have different services. We're back to kind of being like AOL and et cetera, where you have different user groups in different services. So there's a lot of this stuff going on. All right. So what can we do about this? Be intentional about using uncommon or not popular services. Try to be local, support open source, pay attention to personal privacy. I'm not going to spend a ton of time on these things, but these are things that we individual users might be able to do if you think that this is a bad thing for the internet overall. There's a lot going on in the IETF space right now in this. I'm actually a member of the Internet Founders Consortium, or whatever they call it, IFCA or whatever it is, which is all the old folks who helped build up the internet in the first place. And we're working on this in that area. I've done presentations at conferences that are not even technology conferences, at like philosophy conferences and stuff on this. So there's a lot of interest in this area. And it's probably something you should think about and decide like where you come down, and not be completely ignorant of the issues. Again, not trying to tell you you should agree with it or disagree with it, just this is something going on, like, know about it. So anyway, all right, let's talk about internet organizations. These are the last 10 slides, 8 slides, whatever it is. We're probably going to end about 10, 15 minutes early after talking about these, which is all good because you're probably tired of listening to me. All right. The Internet Society, I was on one of the various boards of the Internet Society for a while, and I really like the Internet Society, a lot of what the Internet Society does. I mean, I don't agree with everything the Internet Society does, but whatever. Whenever two or more are gathered and they agree on everything, one of them is redundant. So that's okay. You shouldn't agree with everyone on everything, and it's cool not to. So even organizations, so it's good. That's where discussions and growth come from, is not agreeing. So anyway, the Internet Society, or as they sometimes call themselves, I can't remember now whether they're trying to be called the Society or ISOC. I think they're trying to be called the Society. But anyway, I don't remember. It's a branding thing, and I don't remember all these things. They're funded through corporate and individual memberships. I'm still a member of a local, not really a local, my closest, I live in Knoxville, and my closest society group is in Washington, D.C., which isn't even close enough to drive through, really. But anyway, So a couple of things that they do are they work to bring the internet to communities that are underserved. This is a very important part of what they do. When I was working a lot with the Internet Society, we were building tons and tons of internet exchange points in Latin America. We were going around and soliciting donations and trying to get people to build internet exchange points in Latin America. The other thing they do is they try to work to increase trust on doing business in the internet. They try to help companies and governments in particular understand the structure of the internet and to work more with the internet. Another thing they do is they provide funding and legal cover for the IETF, the Internet Engineering Task Force, which we'll talk about a little bit more. Now, another thing that you might get into that are very interesting, and I really enjoy, are regional users groups. I don't go to these as much as I used to, and I should go to these more. I used to speak at Chinog all the time and LACNOG all the time, and I've spoken at APNOG or APNIC once or twice, and at RIPE, and even at NANOG. So I've actually spoken at all of these except at AFNOG. But anyway, these are great organizations. They do a lot of training and they do a lot of coordination and understanding of how the internet works. RIPE NCC has a thing called RIPE Atlas. The Atlas is a great system that goes out and takes measurements to DNS servers throughout the internet to give you a sense of where hotspots are and stuff. I have a RIPE Atlas probe sitting right up here in the back corner of my office, so I participate in that. I actually let them use my home network to do probes and stuff. NANOG is the North American Network Operators Group. If you're in North America, it's a great group. Again, I don't agree with everything that goes on there, but overall, generally good people. LACNOG is Latin America. CHINOG is Chicago, US. Asia Pacific is APNIC. They generally meet in New Zealand, Australia, someplace around there, Singapore or something like that. AFNOG is Africa. So there's all these regional user groups. And if you go to their web pages, like NANOG has an entire training session series on YouTube and stuff, and RIPE does, and they record all their presentations from all of their past meetings and post them out publicly. So they're really great for these things. All right, standards bodies are, of course, a very important part of the global internet. The IEEE is largely layer 1 and layer 2. This is Ethernet and Aloha and all those kinds of things, DWDM, although there are spin-offs of these now that do a lot of Ethernet, the Ethernet Alliance and stuff like that. But this is all layer 1 and layer 2. I think I have, maybe I don't. The IEEE is a voting-based organization. You have to be a member of a company that has a membership to participate. Individuals can participate, but I find it to be kind of expensive myself to join the IEEE as an individual. W3C is the group that standardizes HTML and XML at large, all markup languages, and those types of things. Largely, anything to do with HTML is done through W3C. This is an open participation organization, volunteer only, so you can actually go to W3C, join a working group, and just work on these standards with people. ITU is another, but they do everything. They do some routing protocols, although they really don't do routing protocols a lot anymore. A lot of the stuff for ISIS is done in the IETF now, but they do some things that are like Ethernet-like, various kinds of layer 2, layer 1 stuff for SATCOM and stuff like that. So the ITU is another one good to be known about. It's an international standards organization. It's very broad based. They do numbering, encryption schemes, all sorts of stuff. They even do like dams and water pipes and like everything. ITU is another one that you kind of have to be a member of an NGO or a company that's doing work in that area. Okay, then we have the IETF, which is on the wire internet protocols. It's an all volunteer organization, very consensus driven, and running code is generally required for standards. Depending on the working group you're in, It can be one implementation or two implementations, whatever it is. We take management security. I've been working in the IETF for over 20 years. We take security, centralization. There's a lot of work going on right now around centralization and energy management in the IETF. We have a very long, difficult process to make standards. And that's because we want them to be well designed and well built. Now, I'm going to walk through some of the IETF stuff here just to give you a sense of how the IETF works. I am currently in the midst of writing an entire series about the IETF on packet pushers. So if you know much about packet pushers, I write a monthly article there, and every other month I've been writing on the process, what the process is in the real world to get standards or documents through the IETF. By the way, there is something up here that I'm going to go back to privacy for just a second. I did write a book in the privacy area that I don't talk about a lot in the technical side because it was my dissertation for a theological degree. So in philosophy, so people might not like my perspective, but it's called Unintended Dystopia. You can just look it up on Amazon. It's called Unintended Dystopia. So that's something, if you're interested in that area, you might want to go check it out along with Shoshana Zuboff and some other people in that space. The Nudge, and there's a bunch of positive and negative books in that area. And if you're really interested in researching that area and understanding it, please feel free to get in touch with me on LinkedIn, and I'll try to give you a list of research papers and stuff that might be useful. Anyway, so the IETF is organized in this way. We have the IESG, the Internet Engineering Steering Group, the IAB, the Internet Architecture Board, and the IRTF, the Internet Research Steering Group, the Internet Research something or another. Anyway, this obviously is all research. This is architectural direction. All the liaisons. Now, I actually did a hedge podcast on this about the IAB and what the IAB does. When I was serving on the IAB, I did a hedge podcast on it. So you might want to look that up if you're really interested in what the IAB does. But essentially, all the liaisons are here to the IEEE. Like if the IEEE is doing a standard and we think it might impinge on something the IETF is working on in encryption or IT or whatever, we have liaisons. We go through and talk to those people and figure it all out. The IESG is all the working group co-chair or all the area directors. So the areas are like art, general, internet, operations, routing, security, and transport. And then under each area, you'll have what's called a directorate, which just basically helps the area directors deal with the flood of documents that come in. And then you'll have working groups like Babel, BESS, OSPF. Babel is being closed. ISIS and OSPF have actually been merged into LSR, link state routing, IDR, which is routing, which is BGP, BESS, which is BGP policy, SFC, MANA, and there's a new one called TVR, time variant routing. So all of these have working group co-chairs and working group mailing lists, and they all have documents that they're working on to figure out like new standards and make things work better and stuff like that. Okay, let me get through the IETF and I'll answer your question, BM, sorry. So the process looks something like this. You do an initial submission, try to get the work group, you present it to the working group. That's fairly easy. Then this takes a lot of socialization and work to get to the working group acceptance. Then you'll normally have an editor assigned here, and the working group will refine the document, which means changing things and doing things to the document to make it, to harden it. Okay, this is a problem. We need to change that bit. This is whatever. All of that happens in the working group refinement. This part might take 10 years. Who knows? It takes a long time to get through this. It may take a couple of years just to get a document accepted in the working group. Then you finally, once you've gone through all of that, everybody in the working group will say, okay, this is ready for publication. It'll go to working group last call. Now in here, you might get, yes, okay. Then it gets a request to publish by the working group co-chairs. there will be a shepherd assigned. Now, the shepherd's job is just to make sure the document makes it through the process. At this point, there will be a directorate review by the AD. The AD will ask the area directorate, somebody who is an expert in that area, to review it, and they will ask experts from other areas to review it. So, for instance, it could be a BGP draft, a draft on the BGP protocol, but it may have security implications. So, the Directorate for Security will be asked, somebody on the security area directorate will be asked to review the document for security stuff. Once you make it through this, you'll get an IETF last call. This is done, there'll be a telechat of the IESG that will say, yes, we'll carry this to a last call, to an IETF last call. There'll be an IESG review. Again, you might be asked to do directorate reviews. Then there'll be an IANA review. Now, what the IANA is going to do is they're going to make sure that you've assigned numbers correctly, names correctly, stuff like that, because IANA manages all the numbers, even down to the port numbers. Like port 80 for HTML, for HTTP is an IANA assignment. IANA actually assigns all that stuff. Then it'll go to the RFC editor, where it'll be checked for grammar and other stuff like that, and then it will be published from there. All right, so that's technically my last slide. So let me pop back over here to this question. Where are the best places to find network design best practices? There are a couple of books I would point you to. I think top-down network design is pretty decent. Oh, darn, there's one by Bruce. I can't remember what that name is. But anyway, you can always look. I have some design stuff in Computer Networking Problems and Solutions book, Art of Network Architecture. And optimal routing design, which is very old at this point, but some people still find it useful. So these three I wrote. I don't remember who wrote this one, but top-down network design is pretty good. I mean, you go all the way back to Halabi's internet routing architectures. I think it's too old now to be extremely useful, in my opinion. A lot of the design patterns are kind of gone. And then Bruce Davies, I think it is, wrote a book on design that's available on the internet, and I don't remember the name of it, but if you email me, I'll see if I can find it. So there's a few different places here. There's a lot of video content that Alvaro and Ethan Banks and I have done here on Safari Books as well, if you want to look for that. All right, so back to the global internet. We talked about all of this last, all these organizations. We started with DNS. We talked about the DFZ providers and access providers and CDNs and edge providers and stuff like that. And then we talked about internet exchanges and these organizations here. So these are systems approach. Oh, yes, systems approach. I've never read the systems approach, 60 years of networking, so I don't know how good it is. I can't recommend or not recommend it. I've heard about it, but I've never actually spent time reading it. Unless, is that Bruce Davies? That might be Bruce Davies. Let me look at it. Yeah, that's Bruce Davies, yes. So if Bruce Davies wrote it, it's going to be pretty good. I like Bruce a lot. I've spent time with him. I worked with him at Cisco. So that's a good book in my opinion. All right. If you want to get in touch with me, I am on LinkedIn. That is the best way to do it. RIW777 if you want to look me up there. Here's some other stuff I've done. Oh my goodness, I don't know what I'm doing next as a live training. I think I'm doing troubleshooting in January. I think I'm skipping November and December and doing troubleshooting in January. And then I think I have a lot of new stuff coming out next year. I'm putting in a lot of proposals right now around coding skills and stuff like that, and some interview skill stuff that I'm doing. And then I'll be redoing this course again next October or so, thereabouts, I think. I'm not entirely certain. You can always follow me on my blog at rule11.tech. I don't blog a ton, but I do try to point at things that I've written other places. I'm not always successful at doing that, but that's what I try to do. And then the hedge, we just finished our 200th episode of The Hedge, which is a networking, computer networking podcast, which you will probably enjoy. I really like that. And somebody said how the internet came to be. I recorded an entire series, about 100 episodes of something called The History of Networking, HON. It's all available up here on the rule11.tech. Some of those are videos, most of those are just audio. And then there's other places I've been trying to find. I know of a couple of other podcasts and a couple of other places that have been writing about this. And like the Internet Founders or whatever it is that I'm a member of has been recording presentations. I've been trying to find those and get those posted up to Rule 11. Not really, just a pointer to those locations so that you can find them. All right. So I think that is it. Feel free to get in touch if you have any other questions. I'll double check for this. And feel free to write in the comments when you do your reviews, like what you'd like to see more of or less of or whatever. These presentations are really hard to put together. They take a long time and they just take a lot of energy and sit down and think about like what should be included and shouldn't. So if you have ideas on something you'd like to see and you didn't see, or there was too much of, or too technical or not technical, please tell me, because I'm really trying to get those done as much as I can. I think that is it for my slides. So I think I can give it back to you, Lindsay, if you want to close out. And tell people
Thank
to say
you, Russ. Oh, go ahead.
I said tell people to say nice things about me.
Okay, please say nice things about Russ. Thank you all for joining us today on how the internet really works. We have recorded today's session, and the recording will be available within 24 hours after we've concluded. Tomorrow, we'll be sending you an email letting you know that today's recording is available. And then also when we close out, if you didn't fill out that brief course feedback survey, we're going to give you an opportunity now. When we end, it will pop up in the center of your screen. So don't close that tab just yet. And please do say nice things about Russ. Thank you, everyone. Enjoy the rest of your day and have a great weekend.